Hey everyone, and welcome back to the Sports Lab. Today, we're putting on our lab coats to break down what is, without a doubt, baseball's most mysterious, most unpredictable, and most maddeningly beautiful pitch, the knuckleball. Have you ever wondered how a pitch thrown slower than most high schoolers' fastballs can leave the best hitters in the world swinging at ghosts? It has a pitch that defies the very logic of the game of sport built on blistering speed, and dizzying spin finds its ultimate puzzle in a ball that has neither. The knuckleball isn't just a pitch, it's a floating, fluttering physics experiment delivered 60 feet, 6 inches at a time. Before we get into the analysis, if you're a fan of the in-depth side of sports, the kind of analysis that goes beyond the box score, please hit that like and subscribe button. It is a huge help, and it allows us to continue bringing these deep dive stories to you, and we want to hear from you. 2. Leave a comment below with a game, a player, or a specific play you think we should break down next. We read every single one. Alright, let's get into the game film. Imagine you're standing in the batter's box. You're a professional, one of the best 750 or so players on the planet at what you do. You've spent your entire life training your eyes and your muscles to react to a baseball. You can recognize the difference between a four-seam fastball and a two-seam fastball by the subtle change in the red seam's rotation. You can pick up the tight spin of a slider, the lazy hump of a curveball. Your brain is a high-speed computer, processing velocity, spin rate, and release point in microseconds to predict where that ball will be in for tenths of a second. You're a master of this craft. And then, the pitcher on the mound winds up, and what comes out of his hand is wrong. It's not fast. It might be traveling at a leisurely 68 miles per hour, and it's not spinning dot at all. The seams on the baseball are perfectly clear, like the markings on a globe that's barely rotating. The ball just floats. It drifts toward you, and your brain screams, "This is it. This is the easiest pitch you'll see all year." It looks like a beach ball, a batting practice lollipop just waiting to be launched into the upper deck. You start your swing, your timing perfect for a pitch this slow. Your hips rotate, your hands come through, the barrel of the bat is on a perfect plane to intercept the ball right in the sweet spot. But then, in the final 10 to 15 feet of its journey, something impossible happens. The ball, which had been on a straight and true path, suddenly lurches down and to the right, as if nudged by an invisible hand. You're already committed. Your bat slices through the empty air where the ball was supposed to be. Strike one. You step out of the box, confused, frustrated. You get back in, determined not to be fooled again. The pitcher delivers the exact same pitch. It floats, it drifts, no spin. Your eyes are locked on it. You wait and wait, anticipating that late dive. But this time, it doesn't dive. It veers to the left. Then it seems to shudder and jump upwards, finishing a good 6 inches higher than you thought it would. You swing under it. Strike two. Now, you have no idea what to do. You're a master craftsman facing a tool that behaves with no discernible pattern. The next one comes in. It dances. It flutters like a butterfly caught in a crosswind, and you take the pitch, hoping it's a ball. The catcher, who is using an oversized mitt that looks more like a high-lie cesta, barely manages to smother it in the dirt. The umpire rings you up. Strike three. You walk back to the dugout, shaking your head, a victim not of speed or spin, but of pure, unadulterated chaos. This is the essence of the knuckleball. It is the great equalizer. It turns powerful home run hitters into flailing novices. It's an anomaly in a game that is increasingly obsessed with quantifiable metrics, spin rate, exit velocity, launch angle. The knuckleball laughs at these metrics. Its spin rate is practically zero. Its velocity is comically low. Its movement is, by its very nature, unpredictable. This has led many to dismiss it, to call it a gimmick or a junk pitch. You'll hear analysts and even some players say it's not a real pitch, that it's a trick reserved for those who can't throw hard enough to compete otherwise. But that perspective completely misunderstands the genius and the science behind it. Calling a knuckleball a junk pitch is like calling a grandmaster's chess strategy, just moving pieces around. It fails to appreciate the profound and complex forces at play. The truth is, the knuckleball isn't an absence of skill, it's a different kind of skill altogether. It's not about overpowering an opponent with raw physical force. It's about mastering an anti-force. It's about a pitcher learning to become a vessel for the chaotic whims of aerodynamics. A fastball pitcher commands the ball. A curveball pitcher manipulates the ball. A knuckleball pitcher unleashes the ball and then hopes for the best, just like everyone else. He has surrendered control in the name of ultimate unpredictability. Over the course of this deep dive, we're going to unravel every aspect of this beautiful enigma. We'll start with the very beginning, the grip, how a pitcher holds the baseball in a way that is so counterintuitive to everything they've ever been taught. From there, we'll become physicists, exploring the invisible forces the Kármán vortex streets, the asymmetric boundary layer separations that make the ball dance. We'll become psychologists, trying to understand the mindset of the hitter, the catcher, and the pitcher himself. This isn't just a pitch, it's a story of physics, art, and the relentless pursuit of an edge in the face of impossible odds. And that story, that pursuit of a chaotic edge, begins not in the powerful muscles of the leg or the shoulder, but in the delicate, precise, and immensely strong tips of the fingers. Before we can even begin to understand the physics of the ball's flight, you have to understand the source of its magic, the grip. The term knuckleball is actually one of the great misnomers in all of sports. You don't throw it with your knuckles. If you tried that, the ball would likely slip out of your hand and travel about 15 feet. No, the knuckleball is a pitch thrown with the fingertips or more, specifically with the fingernails dug into the unforgiving leather of a Major League Baseball. Let's build the grip together. Picture yourself holding a baseball. To throw any normal pitch, a fastball, a slider, a changeup, you cradle it comfortably in your hand, your fingers lying across the seams to get a good feel. Your wrist would be loose, ready to snap and generate spin at the point of release. Now, forget all of that. To throw a knuckleball, you must fight every single one of those natural instincts. You start by digging the nails of your index and middle fingers, and sometimes the ring finger as well, directly into the surface of the ball. You aren't resting them on top. You are actively pressing down, using your fingers like talons to get purchase. The goal is to create a rigid, stable platform. Your thumb and your pinky finger then come up from underneath, acting like a scaffold, gently supporting the ball's weight and keeping it from moving. The result is a grip that looks more like a claw, something tense and unnatural. There's no comfort in it. It's a grip of pure function, designed for one purpose and one purpose only: to kill spin. This grip is the foundation for the second and arguably most crucial part of the process, the release. You see, the spin on a conventional pitch is generated by the pitcher's fingers rolling off the side of the ball as it leaves the hand. For a fastball, the fingers pull straight down, creating backspin that helps the ball defy gravity. For a curveball, they snap over the top, creating topspin that makes the ball dive. The knuckleball requires the exact opposite. The pitcher must deliver the ball with a completely stiff wrist and push it towards the plate. Imagine trying to shove a floating object directly forward in a pool of water without making it rotate. That's the feeling. The fingers extend straight ahead, launching the ball from its perch without imparting any rotational force. It's less of a throw and more of a launch, a catapult, a forward press. This is why the margin for error on a knuckleball is so astronomically small. If the pitcher's wrist snaps even a few degrees, the pitch will start to spin. If it spins, it becomes a 70 miles per hour fastball with no movement of batting practice pitch that will get hit a very, very long way. The entire enterprise hinges on the ability to execute this unnatural, rigid push release over and over again for 100 or more pitches in a game, under immense pressure. One of the fascinating things about this grip of chaos is that while the principle remains the same, the application is intensely personal. There's no one right way to do it. Take a look at the Masters. Tim Wakefield, the iconic Boston Red Sox pitcher, used a defingered grip. He would dig his index and middle fingernails into the top of the wide horseshoe seam. His push was gentle, almost delicate, and it resulted in his famous butterfly knuckleball that would float in at 65 miles per hour and dance with a mesmerizing, almost slow-motion unpredictability. Now, contrast that with R.A. Dickey, who won a Cy Young Award with the pitch. He also used the fingers, but his were spread farther apart, and he drove his nails into the ball with so much force that they would often bleed during games. His release was far more aggressive, a violent shove that launched the ball at 75-80 miles per hour. His pitch didn't flutter. It trembled and broke with a vicious, angry sharpness. Go back even further to Hall of Famers like Phil Niekro and Hoyt Wilhelm. They were often proponents of a three-fingered grip, believing that adding the ring finger to the top of the ball provided more stability and a more consistent release point. It was a trade-off, perhaps a bit less potential for wild, erratic movement in exchange for a higher probability of throwing a true no-spin pitch. On any given delivery, each pitcher has to go through a period of intense experimentation, a lonely journey of trial and Air to find the grip that fits their specific hand size, finger length, and nail strength. And this brings us to a common misconception you'll hear, because the pitch is slow. People assume it's easy on the body, a lazy way to pitch. While it certainly saves the shoulder and elbow from the strain of throwing 95 miles per hour fastballs, the idea that it's physically easy is a complete myth. The strain is simply relocated to maintain that rigid, claw-like grip and execute that perfect push. A knuckleballer has to develop extraordinary strength in their fingertips, hands, and forearms. R.A. Dickey's workout routines for his hands were legendary, involving specialized grip strengtheners and exercises designed to build the kind of endurance needed to dig his nails into leather for hours at a time. It's a different kind of athletic strength, not explosive power, but sustained, precise tension. It is the strength of a surgeon combined with the endurance of a marathon runner, all focused on the last few inches of their fingers. This unique grip, this anti-throw, is the key that unlocks the door to the bizarre aerodynamic world the knuckleball lives in. It is the human input that sets the stage for physics to take over and perform its chaotic ballet. And the entire goal of that human input, of that strange claw-like grip and that unnatural rigid push, is to achieve one single foundational goal that stands in direct opposition to the entire philosophy of modern pitching, the deliberate and almost complete elimination of spin. To truly grasp how revolutionary and bizarre this concept is, you first have to understand that spin is the engine, the language, and the very soul of every other pitch in a pitcher's arsenal. Spin is what turns a thrown object into a weapon. It's what allows a pitcher to bend reality. Think about a major league fastball. When you see a flamethrower rear back and unleash a 98-mile-per-hour heater, it isn't just the velocity that makes it so difficult to hit, it's the spin. A foreseen fastball thrown by an elite pitcher can have a backspin rate of over 1,500 revolutions per minute, or RPM. This rapid backspin creates a pressure differential in the air around the ball, a concept we'll dive into called the Magnus effect. This effect generates lift, causing the ball to fight against gravity and stay on a flatter plane than a non-spinning object would. It's what gives the pitch life, or the illusion of rising as it approaches the plate. Hitters train their entire lives to hit an object that falls at a predictable rate due to gravity. A high-spin fastball breaks that rule. Now, consider the opposite, the curveball. The pitcher snaps their wrist over the top of the ball, imparting a tremendous amount of topspin, often approaching 3,000 RPM. This creates the same Magnus effect, but in the opposite direction, generating a downward force that makes the ball dive violently at the last moment. The iconic 12-6 drop that buckles a hitter's knees is nothing more than applied physics, engineered entirely by spin. Sliders, cutters, sinkers, every single one of them is a variation on this theme. Each pitch is defined by the speed and axis of its spin, which is meticulously honed by the pitcher over thousands of hours of practice. They are, in essence, spin artists. The knuckleball is heresy. It is a complete rejection of this fundamental doctrine. The knuckleball pitcher is not a spin artist. They are a spin assassin. Their goal is not to achieve 2,500 RPM, but to get as breathtakingly close to zero as humanly possible. A good, effective knuckleball will make less than one full rotation on its entire 60-foot, 6-inch flight from the pitcher's hand to home plate. A perfect one, the kind that leaves hitters and catchers dumbfounded, might only complete a quarter or a half of a rotation. It is an exercise in subtraction, in taking away the very thing that every other pitcher is trying to add. It is like a chef deciding to create a gourmet meal by removing flavor instead of adding it. It's a beautifully counterintuitive approach to solving the problem of getting a hitter out. In our modern StatCast era, you can see this difference quantified in stark, beautiful detail. You'll be watching a broadcast, and the analytics graphic will pop up on the screen. You'll see the ace's fastball registered at 2,600 RPM. Then you'll see his devastating slider at 2,800 RPM. The numbers are a testament to his power and skill. If a knuckleballer were on the mound, that same graphic would display a number that looked like a data error, 80 RPM, maybe 50 RPM. On a great one, it might be as low as 30 RPM. And even that minuscule amount of rotation isn't generated on purpose. It's the unavoidable, residual tumble that occurs when a physical object is pushed from a human hand. You can see the difference with your own eyes. A fastball is a red blur. A slider is a tight, spinning dot. A knuckleball, you can see the seams. You can watch the signature of the commissioner of baseball slowly, lazily, drunkenly wander across the surface of the sphere as it floats toward the plate. That visual cue is the first sign to the hitter that all the rules they know are about to be broken. Their brain's high-speed prediction model, built to interpret spin, has just been fed a null set. It has no data to process. Now, here's a deeper insight that challenges the common understanding of the pitch. The goal is the elimination of stabilizing spin, but not necessarily the elimination of all movement. The truth is, achieving absolute zero rotation is physically impossible. There will always be a slight tumble. But this isn't a bug, it's the most critical feature. That slow, quarter turn or half turn rotation is precisely what makes the pitch so unpredictable. If the ball were a perfect, non-rotating sphere with no seams, its flight would actually be more stable. It's the combination of the lack of gyroscopic, stabilizing spin and that slow, clumsy tumble that allows different parts of the ball's uneven surface, namely the 108 raised stitches, to be presented to the oncoming air. This constant, slow change in surface orientation is what triggers the chaotic aerodynamic forces that we're about to explore. By killing the spin, the pitcher strips the ball of its primary guidance system, leaving it vulnerable and susceptible to the slightest whisper of air pressure. The anti-spin principle doesn't make the ball dead, it makes it alive in the most chaotic way imaginable. And the source of that life, the engine of that chaos, isn't some magical or unknowable force. It is a feature that has been hiding in plain sight on every baseball since the game was invented. It's woven directly into the skin of the ball itself, the 108 raised red stitches. To understand the knuckleball, you have to stop thinking of a baseball as a perfect sphere. In the world of aerodynamics, it's anything but. A baseball is a complex, beautifully imperfect object, and its imperfections are the key to everything. Let's put one under the microscope. At its heart is a core of cork and rubber. This is wrapped in multiple layers of tightly wound wool and cotton yarn, creating the dense, solid object we know. The final step is the cover. The interlocking pieces of cowhide, shaped like a figure 8, are stretched over the yarn and hand-stitched together, and those stitches are what matter. A regulation baseball has 108 individual stitches, and they are not flush with the leather. They are raised by about 3/100ths of an inch. That sounds like a tiny, insignificant measurement, but to a fluid like air flowing over a surface at 70 miles per hour, that's not a bump. It's a mountain range. The pattern of these stitches forms the iconic repeating horseshoe or C shape, creating a predictable yet complex topography across the ball surface. Now, on any other pitch, these stitches play an important but secondary role. Think back to our 2,500 RPM fastball. As the ball spins, the seams act like the blades of a tiny propeller, gripping the air and helping to generate the Magnus effect that makes the ball move. A four-seam fastball, where the ball is gripped so that four seams cross the flight path with every rotation, cuts through the air more cleanly and generates efficient backspin. A two-seam fastball, gripped across the narrow part of the seams, has a different interaction with the air, causing it to sink and run. But in all these cases, the ball is spinning so incredibly fast, more than 40 times every second, that the effect of any individual stitch is completely averaged out. The oncoming air doesn't interact with one specific part of the ball surface. It interacts with a uniformly rough, rapidly rotating object. The effect is stable, consistent, and, for the pitcher, controllable. With a knuckleball, this entire dynamic is flipped on its head. By removing the spin, you take away that averaging effect. The stitches are no longer a secondary feature that influences a primary force. They become the primary force themselves. Without the stabilizing gyroscopic spin, the air is no longer dealing with a generalized rough surface. It is now forced to contend with the specific, unique landscape of whichever part of the baseball happens to be facing forward. At that precise moment, the 108 stitches transform from propeller blades into a series of tiny, unpredictable rudders and spoilers. To really see this, imagine a classic wind tunnel experiment. Let's say you suspend a perfectly smooth sphere, like a cue ball, in the middle of the tunnel and release streams of colored smoke to flow over it. You see the smoke streams travel smoothly over the front surface and then detach from the back in a relatively symmetrical and predictable pattern. Now, let's swap the cue ball for a baseball. Well oriented so the wide part of the seam is facing directly into the wind. As the smoke streams approach the ball, they hit that raised wall of stitches and everything changes. The flow is tripped. It becomes chaotic and turbulent. You would see the smoke on one side of the ball behaving completely differently than the smoke on the other. The wake behind the ball would become a messy, asymmetrical swirl of vortices. Now for the final step, Imagine that baseball is now rotating, but incredibly slowly, just like a real knuckleball. One moment, a smooth patch of leather faces the wind. The next, a horseshoe seam tumbles into view. The point at which the airflow is tripped from smooth to turbulent is constantly and randomly shifting from the top of the ball to the bottom, from the left to the right. This creates a constantly changing asymmetrical wake behind the ball, and since for every action there is an equal and opposite reaction, this unbalanced wake pushes back on the ball, shoving it randomly in different directions. The stitches are literally stirring the air into a chaotic soup, and the ball is tossed about in the turbulence it creates. This reliance on the ball's surface imperfections leads to a fascinating bit of counterintuitive baseball wisdom. You would think a knuckleball pitcher would want a brand new, perfectly pristine baseball every time, but that's not always the case. Many of the great knuckleballers, like the Negro brothers, were known to subtly prefer a ball that was slightly scuffed or had some minor wear and tear. Why? Because a tiny scuff on the leather acts like an extra stitch. It's another tripwire for the airflow, another potential source of chaos. While a conventional power pitcher might ask the umpire to throw out a scuffed ball because it feels wrong in his hand or might affect his grip, a knuckleballer sees the same scuff as another potential weapon in their arsenal. It's a perfect illustration of the opposing philosophies. One seeks to impose perfect, repeatable order on the ball. The other seeks to find and exploit every opportunity for chaos, right down to the microscopic flaws on the cowhide. The 108 stitches are the foundation of this chaos, the architecture of unpredictability. But for that architecture to even matter, for those 108 stitches to become the primary actors in this drama, a much larger and more powerful force has to be completely removed from the stage. That force is the ghost in this machine, the dominant physical principle in pitching that the knuckleball is famous for defying, the Magnus effect. If you've ever wondered what makes a curveball curve or a slider slide, the answer, in a word, is Magnus. Understanding this force is the key to understanding just how radical and defiant the knuckleball truly is. So, let's break it down. The Magnus effect describes the force exerted on a spinning object moving through a fluid. In this case, a spinning baseball moving through the air. Imagine a ball is thrown with a heavy topspin, like a classic curveball. As the ball travels forward, the top surface of the ball is rotating in the same direction as the oncoming air. This motion drags the air along with it, causing the air to speed up as it passes over the top on the bottom of the ball. The opposite is happening. The surface is rotating against the oncoming air, creating friction and slowing the airflow down. So now you have a situation where the air is moving quickly over the top of the ball and slowly underneath the ball. This is where another famous scientific principle, Bernoulli's principle, comes into play. It states that faster moving fluid exerts lower pressure and slower moving fluid exerts higher pressure. Because the air is moving slower underneath our spinning curveball, it's creating a pocket of high pressure. Because the air is moving faster over the top, it's creating a pocket of low pressure. The universe doesn't like this imbalance. The ball is then pushed from the area of high pressure to the area of low pressure. For our curveball, that means a powerful downward push. That is the Magnus force. That is the invisible hand that grabs the baseball and yanks it toward the dirt long after it has left the pitcher's control. This same principle governs every other spinning pitch. A fastball with heavy backspin creates the opposite effect: high pressure on top, low pressure on the bottom. This generates an upward Magnus force that counteracts gravity, making the ball seem to ride or hop through the strike zone. A slider or cutter, thrown with a combination of backspin and sidespin, often called gyroscopic spin, generates a Magnus force that pushes the ball sideways, causing a late, sharp, lateral break. A pitcher who can generate a high spin rate is, effectively, an expert at maximizing the Magnus effect. They are using science to create predictable, powerful, and controllable movement. And now you see the knuckleball's genius. By throwing a pitch with almost no spin, the knuckleball pitcher performs an act of aerodynamic sabotage. He completely nullifies the Magnus effect without any significant, consistent rotation. There's no way to create that stable pressure differential between the two sides of the ball. There's no fast lane and slow lane for the air. There's no high pressure zone to push from and no low pressure zone to push to. The single most powerful and predictable force that can act on a baseball in flight has been systematically and surgically removed from the equation. The king has been dethroned. To appreciate how unique this method is, consider another pitch that has a strange relationship with the Magnus effect, the mythical Gyroball. Popularized by Japanese pitchers, the gyroball is thrown with a perfect spiral spin, like a bullet or a football, with the axis of rotation pointing directly at the batter. Because the spin is perfectly aligned with the direction of travel, there is no traditional topspin, backspin, or side spin component relative to the oncoming air. In theory, this also cancels out the Magnus effect, causing the ball to drop due to gravity, but without the sharp break of a slider. It was another way to defy a hitter's expectation. But notice the difference in philosophy. The gyroball attempts to neutralize Magnus through perfect, maximized high-speed spin on a specific axis. The knuckleball achieves the same end through the near total absence of spin altogether. This brings us to the most critical insight. You might think that by removing the Magnus effect, the ball would become more predictable, not less. Without that force pushing it around, shouldn't it just travel in a straight line, pulled down only by gravity? This is the paradox of the knuckleball. The Magnus effect is so immensely powerful that on a normal pitch, it completely overwhelms all the other, much smaller aerodynamic forces. It's the sun in the aerodynamic solar system. Its gravity dictates the orbit of everything else. When you remove it, when you extinguish that sun, you don't get cold, stable darkness. You get chaos. You create a power vacuum. All of those tiny, subtle, previously insignificant forces, the ones generated by the 108 stitches tripping the airflow, the ones generated by the asymmetric weight behind the ball, are suddenly free to exert their influence. They rush in to fill the void left by the ups of Magnus. Force. The knuckleball's magic isn't just about what it is, it's about what it isn't. By stripping the ball of its primary guidance system, the pitcher turns it into a rudderless ship, at the mercy of every tiny crosswind and eddy current it creates on its journey to the plate. So let's talk about those tiny crosswinds and eddy currents. To understand the forces that rush in to fill the power vacuum left by the Magnus effect, we need to zoom in on the air itself. We need to look at the two fundamental states it can exist in when it meets a moving object. It can behave with smooth, predictable order, or with swirling, unpredictable chaos. In the world of fluid dynamics, these two states are known as laminar flow and turbulent flow, and the knuckleball exists in the violent, beautiful space between them. To make this simple, let's use an analogy. Imagine a very wide, deep, and slow-moving river. The water is flowing perfectly without any disturbances. If you were to release dye into it, the dye would travel in straight, clean, parallel lines. The layers of water slide past each other smoothly. This is laminar flow. It's orderly, it's predictable, and it creates very little drag. It is the kind of smooth stream you see when you first turn a faucet on just a trickle. Now, in the middle of that perfect river, let's place a large, jagged boulder. What happens to the water downstream from the boulder? It's no longer smooth. It churns, it swirls, it forms chaotic eddies and vortices. The dye you release would be instantly mixed into an unpredictable mess. This is turbulent flow. It's chaotic, it consumes a lot of energy, and it creates a significant amount of drag. It's the gushing, messy stream you get when you crank the faucet on full blast. Every object that moves through the air, whether it's an airplane wing, a car, or a baseball, is a boulder in a river of air, and it creates a combination of these two flows. The thin layer of air immediately touching the object's surface is called the boundary layer. Right at the front of the baseball, the air splits and begins to flow around the sides. Initially, this boundary layer is smooth and orderly, it's in a laminar state, but as the air continues to flow around the curved surface of the ball, it begins to lose energy and can no longer hug the surface. At a certain point, it will detach or separate from the surface. And this is where the flow transitions from smooth and laminar to chaotic and turbulent. The key to understanding why an object moves the way it does is to understand where and how this separation happens. This is where the knuckleball speed becomes so incredibly important. The transition from laminar to turbulent flow is heavily dependent on the velocity of the object. Scientists have a way of measuring this called the Reynolds number. But what's important for us to know is that there are different aerodynamic regimes at different speeds. At very high speeds, like that of a 95 miles per hour fastball, the airflow over the baseball becomes turbulent very quickly and very close to the front of the ball. This actually creates a more stable flight path. It is the same reason golf balls have dimples. The dimples are designed to intentionally trip the boundary layer into a turbulent state right away, which ironically reduces overall drag and allows the ball to travel farther. At the other extreme, at very low speeds, the airflow might remain laminar over a much larger portion of the ball surface, leading to a wide, predictable wake. But the knuckleball is thrown in a very specific velocity window, typically between 60 and 75 miles per hour. This speed places it in a precarious position known as the critical Reynolds number regime. It's a transitional zone. The airflow around the ball is aerodynamically unstable. It hasn't decided if it wants to be smooth and laminar or chaotic and turbulent. This makes the separation point, the spot where the flow detaches, incredibly sensitive to any minor disturbance. And what is the biggest disturbance on the surface of a baseball? The 108 raised stitches. Remember our boulder in the river? The stitches are a series of smaller, constantly moving boulders. As the smooth, laminar boundary layer flows over the front of the knuckleball, it is desperate to stay attached to the surface, but then it encounters the sharp, raised edge of a seam. That seam acts as a tripwire. It violently forces the smooth flow to separate from the surface and erupt into a turbulent, chaotic mess. Because the knuckleball is slowly tumbling, the location of this tripwire is constantly changing. For a split second, a seam at the top of the ball triggers turbulence there. An instant later, as the ball rotates a quarter turn, a seam on the side of the ball becomes the new trigger point. The result is a baseball flying through the air while being surrounded by a constantly shifting, asymmetrical cloud of laminar and turbulent flow. This brings us to the crucial insight. When most of us think of turbulence, we think of drag, a force that slows things down. But for the knuckleball, it's not the amount of turbulence that matters, but the imbalance of it. It's the asymmetry that creates the force. When the airflow on the left side of the ball separates and becomes turbulent before the right side does, it creates a swirling, low-pressure wake on that left side. This pressure difference between the two sides creates a net force that shoves the ball to the right. A fraction of a second later, a seam tumbles into a new position, tripping the flow on the bottom of the ball. Now a low-pressure wake forms there, and the ball gets a tiny push upwards. The fluttering, dancing motion of the knuckleball is a direct result of this continuous series of tiny, random, unbalanced pushes, all generated by the unstable and unpredictable transition between two different states of air. While some of those pushes and shoves are indeed random, born from the chaotic transition of airflow, there's one specific, surprisingly rhythmic pattern of chaos that often emerges in the wake of a bluff body object like a baseball. It has a wonderfully evocative name that sounds like it is straight out of a spy novel, the Kármán vortex streak. This phenomenon is a key ingredient in our chaotic recipe, and it's directly responsible for the knuckleball's signature side-to-side wobble. To understand this, you don't need a wind tunnel. You just need to look at a flag flapping on a windy day. The flagpole is a cylinder, a non-aerodynamic shape standing in a moving fluid, the air. As the wind rushes past the flagpole, the air can't hug the sharp curve to the back, so it has to separate. But here is the fascinating part. It doesn't separate from both sides at the same time in a clean, symmetrical way. Instead, a small whirlpool of air, called a vortex, will form on one side, let's say the top side, and then peel off or shed into the wake. The formation of this vortex creates a small pocket of low pressure on the top side of the flagpole. A split second later, the process repeats on the opposite side. A vortex forms on the bottom side and sheds into the wake, creating a low pressure pocket there. This happens in a continuous, alternating sequence. A vortex sheds from the top, then the bottom, then the top, then the bottom, over and over again. This staggered, repeating pattern of swirling vortices trailing behind the object is the Kármán vortex streak. Now, think back to our flag. When the vortex sheds from the top, the low pressure pulls the flag fabric slightly upwards. When the next vortex sheds from the bottom, the low pressure pulls the flag downwards. This rapid, rhythmic, alternating push and pull is what causes the flag to flap back and forth. The flag is simply making the invisible dance of the air visible. A non-spinning baseball, flying at the right speed, behaves exactly like that flagpole. It's a sphere, a classic bluff body, and as the air rushes past it, it sheds a Kármán vortex streak into its wake. A vortex peels off the left side, creating a low-pressure zone and giving the ball a tiny nudge to the left. An instant later, a vortex peels off the right side, creating another low-pressure zone and nudging the ball to the right. Left, right, left, right. This is the scientific explanation for the mesmerizing shimmy or wobble you see on a great knuckleball. It's the atmosphere playing a high-frequency drumbeat on the back of the baseball, causing it to oscillate as it flies. And don't mistake this for a weak or insignificant force. The cumulative, effect of a Kármán vortex street can be astonishingly powerful. The most dramatic and tragic example of this is the collapse of the Tacoma Narrows Bridge in 1940. The bridge, nicknamed Galloping Dirty for its tendency to undulate in the wind, was built with a solid, flat deck. On a day with a steady wind of only about 40 miles per hour, the wind flowing over and under the bridge deck began to generate a massive Kármán vortex street. Vortices shed from the top of the deck, then the bottom, in a steady rhythm. This created an alternating up and down force by a disastrous coincidence. The frequency of this vortex shedding perfectly matched the natural resonant frequency of the bridge's structure. Each tiny push from the vortices added energy to the bridge's oscillations, making them bigger and bigger, until the bridge began to twist and tear itself apart in a spectacular display of aerodynamic power. While the force on a 5-ounce baseball is obviously not going to rip it to pieces, it's the exact same physical principle at work, and it is more than powerful enough to make that baseball dance unpredictably on its way to the plate. Now, after hearing all this, you might be thinking, okay, so the movement isn't random after all. It's just a rhythmic, predictable wobble. This is where we have to add another layer of beautiful complexity on a perfectly smooth, non-rotating sphere. In a perfectly stable wind, the Kármán vortex street would indeed be quite regular, but as we know, a baseball is not a smooth sphere. It has 108 stitches, and on a knuckleball, it's also undergoing a slow, clumsy tumble. These two factors, the seams and the slow rotation, are constant disruptors of this rhythmic dance. They act as sources of random noise in an otherwise semi-predictable system. A seam rotating through the wake can break up a vortex before it fully forms. It can cause a vortex to shed earlier or later than its natural rhythm would dictate. It can make one vortex stronger than the last. This constant interference from the seams prevents a stable, predictable vortex streak from ever truly locking in. So what you end up with is a hybrid motion. You have the tendency for a side-to-side wobble, provided by the baseline physics of the Kármán vortex streak, while layered on top of that is the pure randomness injected by the seams. This is why the knuckleball's flight is so impossible to track. It will shimmy back and forth for a few feet, and then just as the batter's brain thinks it has the pattern time, the seam will interfere and the ball will suddenly dart 6 inches or drop off a table. It's a perfect marriage of rhythmic chaos and pure, unadulterated randomness. And the source of that pure, unadulterated randomness, the force behind the sudden darts and dives that often defy even the semi-predictable rhythm of the Kármán vortex streak, comes from an even more fundamental and unstable process. It's a concept we touched on earlier, but one that deserves its own spotlight because it is arguably the primary engine of the knuckleball's most shocking movements. It all comes down to the wildly unstable and asymmetric separation of the boundary layer. Let's quickly revisit that concept. Remember, the boundary layer is that incredibly thin sheet of air that is literally clinging to the surface of the moving baseball, and this layer can exist in one of the states: smooth and orderly laminar flow, or chaotic and churning turbulent flow. The single most important event in the flight of a non-spinning ball is the moment of separation, the point on the backside of the ball where this boundary layer can no longer hold on and detaches, creating the wake. The size, shape, and pressure of this wake are what determine the forces acting on the ball. Here's the crucial and somewhat counterintuitive piece of physics you need to understand. A smooth, low-energy laminar boundary layer is actually quite weak. It doesn't have the energy to fight the rising pressure as it flows around to the back of the ball, so it gives up and separates relatively early, close to the ball's equator. This early separation creates a very large, wide wake behind the ball, which in turn results in a large amount of pressure drag. Now consider a chaotic, high-energy turbulent boundary layer. All that churning and mixing brings high-velocity air from outside the layer down to the surface. This injection of energy makes the turbulent boundary layer stronger. It can fight against that rising pressure for longer, allowing it to stay attached to the ball's surface farther round to the back before it finally separates. This late separation creates a much smaller, narrower wake, which results in significantly less pressure drag. It is a strange paradox of aerodynamics. The more chaotic the flow is right next to the ball, the sleeker and more efficient the ball's overall passage through the air becomes. Now, let's apply this paradox to our slowly tumbling knuckleball as it flies. It's in that critical speed zone, where its boundary layer is on a knife's edge, ready to be either laminar or turbulent. And what's the trigger? The stitches. Imagine a knuckleball in mid-flight. On the left side of the ball, The surface facing the wind is a smooth patch of white cowhide. The boundary layer on this side remains in its fragile, laminar state. On the right side of the ball, a raised seam is oriented directly into the airflow. This seam acts as a tripwire, forcing the boundary layer on the right side to transition violently into a turbulent state. So now you have this completely unbalanced, asymmetrical situation. On the left side, you have a weak, laminar boundary layer that separates early, creating a big, wide, high-drag wake. On the right side, you have a strong, turbulent boundary layer that separates late, creating a small, narrow, low-drag wake. This imbalance creates a massive pressure differential. The large, high-pressure wake on the left side acts like an invisible hand, pushing the baseball away from it. The ball is shoved, suddenly and sharply, from the high-pressure side towards the low-pressure side. In this instance, it darts to the right. A tenth of a second goes by. The ball completes a quarter rotation. Now, the seam that was on the right is on the bottom. The process repeats, but in a different direction. Now you have a turbulent boundary layer on the bottom and a laminar one on the top. The big, high-pressure wake is now on top, and the invisible hand gives the ball a sharp, downward shove. This is the source of the knuckleball's signature late, unpredictable break. It's not a curve, it's a shove. It's a series of discrete, directional pushes generated by a constantly shifting imbalance in the ball's own wake. This then begs the question, which force is in charge? Is it the rhythmic Kármán vortex streak causing the wobble? Or is it this asymmetric boundary layer separation causing the darts and dives? The answer, and the reason for the pitch's ultimate inscrutability, is that it's both, and neither. All of these forces are happening at the same time, competing for dominance. You might have a Kármán vortex streak trying to establish its gentle side-to-side rhythm, but then the ball tumbles just right, a seam trips the boundary layer, and a powerful asymmetric separation event completely overpowers the wobble and sends the ball diving 6 inches. The slow, unpredictable tumble of the baseball is the conductor of this chaotic orchestra, constantly changing the instrument that is playing the lead melody. It's why you can't predict the flight path. The hitter's brain isn't trying to solve for one variable. It is trying to solve a multivariable equation in real time where the variables themselves are constantly changing. It's a beautiful, unsolvable problem delivered at 70 miles per hour. And if the slow tumble of the ball is the conductor of this chaotic orchestra, then the instruments that play the wild, unpredictable notes are the seams themselves. We've talked about them as tripwires and disturbances, but to truly appreciate their role in real time, it's even more accurate to think of them as a series of 108 tiny unpredictable rudders, each one capable of steering the ball onto a new and unplannable course. Think about how a rudder on a boat works. It's a simple, flat plane that you place in the flow of water at the back of the vessel. When the rudder is straight, the water flows past it symmetrically, and the boat travels in a straight line. But when you angle the rudder, you deflect the flow of water. This deflection creates a pressure difference on either side of the rudder, and that pressure difference pushes the stern of the boat, causing it to turn. The greater the angle of the rudder, the sharper the turn. It's a very direct and controllable system. The seams on a slowly rotating knuckleball function in a remarkably similar way, but with air instead of water, and with one crucial difference: the pitcher has absolutely no control over them once the ball is released. Each raised stitch that tumbles into the path of the oncoming air acts like a rudder. It deflects the airflow, it disrupts the boundary layer, and it triggers the asymmetrical separation. That generates a push. The critical factor, just like with the boat's rudder, is the orientation. The angle at which the seam meets the wind determines the direction and the magnitude of the force. Let's really break this down. Imagine a seam that, for a brief moment, is oriented perfectly perpendicular to the airflow. It presents a blunt, vertical wall to the air, creating a significant and relatively symmetrical disturbance. Now, imagine a moment later, the ball has tumbled slightly, and a different part of the seam is now almost parallel to the airflow. It acts more like a sharp fin, slicing through the air. The disturbance it creates is far more subtle, and the force it generates will be completely different. And then you have every possible angle in between. A seam at a 45-degree angle will trip the boundary layer in a totally different way than one at a 70-degree angle. Now, add in the complexity of the baseball stitch pattern. It's not a simple grid. It's that iconic, repeating C or horseshoe shape. This means that as the ball completes its slow, lazy rotation, it isn't just presenting a seam or no seam to the wind. It's presenting a complex curve of stitches. with the angle of attack on the air constantly changing along the length of that curve. This is what allows for the infinite variety of movements. Let's trace the journey of a single knuckleball to make this crystal clear. The pitcher releases it, and it begins its 60-foot journey with a slow, quarter rotation per second tumble. For the first 15 feet of its flight, let's say the wide, flat part of the horseshoe is facing directly forward. This orientation might cause the airflow to separate symmetrically above and below the ball, creating a net downward force. The ball begins to sink, looking like a simple chang-up. The batter's brain registers this, okay, sinking pitch. But then, for the next 15 feet, the ball tumbles about 45 degrees. Now, the sharp corner of the horseshoe is the leading edge. The seams are now angled relative to the wind, one trailing up into the left, the other down into the left. This might trigger a turbulent separation exclusively in the upper left quadrant of the ball. The result? A strong aerodynamic push down and to the right. The pitch that was sinking is now darting away from a right-handed batter. The batter's brain has to throw out its first calculation and start a new one. For the final, critical 20 feet, the ball tumbles again. Now, the smooth white leather is facing forward, but the seams that were at the front are now on the sides of the ball, in the perfect position to interfere with the Kármán vortex street we talked about. They disrupt the rhythmic shedding of vortices, causing the gentle wobble to suddenly transform into a violent, unpredictable shudder. The pitch that was sinking, then darting, is now finishing with a convulsive shake. And this leads to the most important philosophical point about the knuckleball, and a direct refutation of a common question. Can a pitcher learn to control this? Can they become so skilled that they can release the ball with a specific seam orientation to guarantee a breakdown in a way? The answer is an emphatic and universal no, and that is the entire point. The pitcher's job is not to control the rudders. Their job is to create the perfect conditions for the rudders to take over. They are focused on one thing and one thing only, launching the ball with as little spin as possible. The initial orientation is set by their grip, but the subsequent tumble, the exact axis of rotation, is subject to the whims of 100 tiny variables. A microscopic difference in the finger pressure at release, a slight puff of wind from the third base side, the humidity in the air, any of these can alter the tumble, just enough to present a completely different sequence of rudder orientations to the air. This is why the pitcher, the catcher, and the batter are all in the same boat. They are all spectators, watching to see what path the ball will chart on this particular journey. The art of the knuckleballer is the art of surrendering control, and a crucial part of surrendering that control, of creating the perfect conditions for chaos to reign, is a paradox in a sport utterly obsessed with power and velocity. The deliberate rejection of speed. The knuckleball doesn't just work in spite of being slow. It works because it is slow. More than that, it only works within a very narrow and specific speed limit, a sweet spot of velocity that is the key to unlocking all the bizarre physics we've been discussing in baseball. Speed is king. Pitchers are trying to throw harder. Hitters are measured by their exit velocity, and the radar gun is often the first stat a broadcaster mentions. So, it seems deeply counterintuitive that the most unhittable pitch in the game would be one that bare lie registers on that gun. The sweet spot for a classic knuckleball is typically between 60 and 75 miles per hour. This isn't a preference, it's a physical necessity, and it's for the fundamental reasons: the physics of time and the physics of air. First, let's talk about time. All the aerodynamic forces we've dissected the Kármán vortex street. The asymmetric boundary layer separation, the steering effect of the seams are incredibly subtle. They are a collection of tiny, almost insignificant pushes and shoves. But over the course of the ball's 60-foot, 6-inch journey, these tiny pushes can add up to create a massive 6-inch dive or a foot-long lateral dart. For this accumulation to happen, the forces need time to act. A baseball's flight is a frantic race against the clock. If a pitcher throws the ball too fast, say at 90 miles per hour, it simply doesn't spend enough time in the air for these delicate, chaotic forces to significantly influence its path. It gets to the plate too quickly. By slowing the pitch down into that 60-75 miles per hour range, the pitcher is buying time. They are giving the atmosphere more opportunity to work its magic. A longer flight time means more vortices shed, more chances for the boundary layer to separate asymmetrically, and more opportunities for the tumbling seams to act as rudders. Time is the canvas upon which the knuckleball's chaotic art is painted. The second reason is more technical, and it goes back to a concept we introduced earlier: the aerodynamic regime. The knuckleball's magic happens in what scientists call the critical Reynolds number regime. This is that unstable, transitional zone where the airflow is on a knife's edge between being smooth and orderly laminar and being fully chaotic turbulent. It's this instability that makes the ball so sensitive to the tiny disturbances caused by the seams, and for an object with the size, mass, and surface roughness of a baseball. This critical regime exists only within that specific 6,075 miles per hour velocity window. So what happens if a pitcher strays outside of this sweet spot? If they throw the pitch too fast, say in the low 80s, they push the ball out of the critical regime. The airflow around the ball becomes fully turbulent much earlier in its flight, and as we've learned, a stable, fully turbulent boundary layer is actually more predictable and results in less drag and less dramatic movement. The pitch loses its signature flutter. It might still have some late sink or run due to the seams, but it behaves more like a dancing fastball than a true, chaotic knuckleball. R.A. Dickey famously lived on the upper edge of this window throwing a harder knuckleball that had a sharper, more violent break, but he was constantly walking a tightrope, knowing that a little too much velocity would kill the pitch's magic. Conversely, if a pitcher throws the ball too slow, say, under 60 miles per hour, they run into a different problem. The aerodynamic forces become weaker at lower speeds, but more importantly, they give the batter a significant advantage. A 58 miles per hour pitch, no matter how much it moves, travels so slowly that a major league hitter's elite vision and reflexes can actually track the movement, process it, and still have time to adjust their swing. The pitch loses its crucial element of deception. This brings us to the hitter's internal clock. A typical major league swing takes about 160 milliseconds. The hitter has to make their decision to swing when the ball is roughly halfway to the plate. A 95 mph fastball gets to the plate in about 400 milliseconds. A 70 miles per hour knuckleball takes nearly 600 milliseconds. That extra 200 milliseconds, or the tenths of a second, sounds like an eternity. But the knuckleball plays a devastating trick on the hitter's brain. Most of its dramatic, unpredictable movement happens in the last 15 to 20 feet of its flight long after the swing. Swing decision has been made, so the hitter uses the first 30 feet of flight to time the pitch, and the ball gives them completely false information. The 70 miles per hour floater they decided to crush is not the 70 miles per hour diver that actually arrives at the plate. The sweet spot is this perfect, malicious balance, slow enough for physics to wreak havoc, but just fast enough that the havoc happens too late for the human brain to possibly react. And here's the final layer of genius. The slow speed of the knuckleball doesn't just optimize its own movement, it's a strategic weapon. While you might think a knuckleballer throws nothing but that one pitch, the best ones, like Hall of Famer Phil Niekro, used it to set up a surprisingly effective fastball. Niekro would throw his 70 miles per hour butterfly over and over, lulling the hitter into that slow, almost passive timing. Then, out of nowhere, he'd throw his fastball. His fastball was only about 81 or 82 miles per hour, well below league average, but to a hitter whose entire system was calibrated for a 70 mph pitch, that 81 miles per hour fastball looked like it was 100. It jumped on them, consistently jamming them or causing them to swing late. The velocity sweet spot, therefore, isn't just an aerodynamic necessity, it's the foundation of a brilliant tactical deception. But even when a pitcher has achieved a state of near perfection, mastering that awkward grip, that spin-killing push release, and that narrow velocity sweet spot, there's a final set of variables they can never hope to control. These are the invisible forces that change not just from day to day or city to city, but sometimes even from inning to inning. We're talking about the weather. For a knuckleballer, the atmosphere isn't just a neutral medium that the ball travels through. It's an active, moody, and fickle participant in the pitch's flight. The slightest change in temperature, humidity, or wind can completely alter the personality of the pitch, turning a masterpiece into a batting practice fastball, or vice versa. The knuckleball is uniquely sensitive to these atmospheric changes because its movement relies on such incredibly subtle and delicate forces, while a 95 miles per hour fastball will power its way through the air, largely indifferent to minor changes in density. A 70 miles per hour knuckleball is completely at the mercy of the air's character on any given day. Let's start with the most direct factor, air density. Air density is simply a measure of how many air molecules are packed into a given amount of space. Colder air is denser, the molecules are huddled closer together. Hotter air is less dense. The molecules are energized and spread farther apart. For a knuckleball, Denser air means there are more molecules for the seams to grab and deflect. This provides more fuel for the aerodynamic engine, amplifying all the forces we've discussed. A pitcher taking the mound on a crisp, cool autumn evening might find their knuckleball has an extra vicious bite to it. The heavy air gives the pitch more to work with, making its dance more dramatic. Conversely, on a sweltering, humid summer afternoon, the air is thinner. There are fewer molecules to interact with the seams, and the resulting forces are weaker. The knuckleball on a day like this might be flatter, less lively, and far more vulnerable to being hit hard. Altitude plays the same role. Pitching a mile above sea level at Coors Field in Denver is a nightmare for most pitchers, and knuckleballers are no exception. The air at that altitude is significantly thinner and less dense. This is why curveballs don't break as much that the Magnus effect is diminished. For the knuckleball, the effect is the same. The seams have less air to push against, and the pitch's movement is severely muted. Now, let's talk about humidity, because it's one of the most misunderstood factors in sports science. The common assumption, the one that makes intuitive sense, is that humid air is heavy or thick. You hear it from broadcasters all the time. The air is heavy tonight. The ball's not going to travel. But in reality, the exact opposite is true. Humid air is actually less dense than dry air at the same temperature. Here's why. Dry air is made up mostly of nitrogen molecules, N2, and oxygen molecules. O2, when the air becomes humid, water vapor or H2O molecules is introduced. If you look at the periodic table, a water molecule is significantly lighter than both a nitrogen molecule and an oxygen molecule. So, as these lighter water molecules enter the air, they displace the heavier nitrogen and oxygen molecules. The result is that a cubic foot of humid air literally weighs less than a cubic foot of dry air. So, from a pure physics standpoint, a humid day, much like a hot day, should result in a knuckleball with slightly less movement. But the most dramatic and obvious atmospheric variable, of course, is the wind. For a power pitcher, a 10 miles per hour crosswind might add a couple of inches of tail to their fastball, a minor adjustment. For a knuckleballer, that same 10 miles per hour wind is a hurricane. Remember, the knuckleball is a rudderless ship launched into the ocean of air. A steady wind is like a powerful ocean current. A breeze blowing from left to right can push the entire trajectory of the pitch a full foot or more to the right. A wind blowing in from center field can slow the pitch down even more, giving the aerodynamic forces even more time to work and potentially making the pitch break even more violently. Now imagine a gusty, swirling wind, like the kind you find in historic ballparks like Fenway Park or Wrigley Field. A pitcher could execute two mechanically identical pitches back to back. The first is thrown into a lull in the wind and flutters over the plate. The second is thrown into a sudden 15 miles per hour gust, and it gets blown a foot and a half outside, sailing past the catcher for a pass ball. This is why knuckleballers like Tim Wakefield were known for being so unpredictable in their home parks. The wind didn't just add to the chaos, it multiplied it exponentially. This brings us to the fascinating human element of it all. You might think a knuckleballer's pre-game routine is just hoping for a good knuckleball day, but the reality is that they become amateur meteorologists. During their warm-ups, they aren't just getting their arms loose, they are diagnosing the atmosphere. They can feel the way the ball floats out of their hand. They can sense the density of the air and how much the ball is dancing. They might get to the bullpen and realize, okay, the air is cool and thick today. The ball has incredible life. I can trust it in the strike zone. Or they might feel the opposite. It's hot, the air feels thin, and my knuckleball is flat today. I can't rely on it. I am going to have to mix in my slow fastball more often and focus on just getting ahead of hitters. Their entire game plan, their entire approach to every batter can be dictated by the weather. It's a constant adaptation, a battle fought not just against the man in the batter's box, but against the invisible, ever-changing environment of the ballpark itself. So while the pitcher is constantly diagnosing and adapting to the external chaos of the atmosphere, they must simultaneously strive for a state of absolute internal consistency and mechanical perfection. This brings us from the macro-level forces of the environment to the micro-level precision of the human body. We arrive now at the heart of the knuckleballer's craft, the single moment of truth where all the physics and all the theory are put into practice. The release of a knuckleball is a profound physical paradox, a feat of biomechanics that goes against every instinct the pitcher has ever developed. To understand this paradox, you have to understand how a conventional pitcher generates force. The entire pitching motion is what biomechanists call a kinetic chain. It is a sequence of movements designed to build and transfer energy from the largest muscles in the body to the smallest, creating a whip-like effect. The power starts in the legs as the pitcher pushes off the rubber. It transfers to the hips and torso as they rotate violently towards the plate. This rotation yanks the shoulder forward, which then pulls the arm through. The final links in this chain are the explosive pronation of the forearm and the violent snapping of the wrist and fingers. This entire sequence, which happens in the blink of an eye, is designed to maximize the velocity and spin imparted on the baseball at the moment of release. The knuckleball pitcher must use this very same kinetic chain. They need to generate enough force from their legs, hips, and torso to get the ball to the plate at a major league speed of 65 to 75 miles per hour. They must maintain the same arm speed and come through the same arm slot as they would for a fastball, because any change in tempo or effort is a dead giveaway to the hitter. But then, in the final, critical millisecond of the delivery, they have to do something completely unnatural. They have to deaden the end of the whip. They have to prevent that explosive snap. It's the equivalent of flooring the accelerator on a world-class race car to build up speed, and then slamming on the brakes and putting it in neutral an inch before it crosses the finish line. This is achieved through two main physical cues we touched on earlier: the locked wrist and the forward push. Throughout the entire forward moving phase of the delivery, the knuckleballer must maintain a completely rigid, almost frozen wrist. Any flexion or extension, the natural snapping motion, will cause the fingers to roll over or under the ball, and the instant that happens, you get spin. This is the single hardest instinct for a pitcher to unlearn. Their body has been trained for a decade or more to snap the wrist for every single throw they make. Resisting this urge requires intense focus and muscle memory. Then comes the release itself. It is not a throw, it is a push. The pitcher's focus is on extending their 2 or 3 fingertips directly at the catcher's mitt, as if they were trying to push a thumbtack into a distant corkboard. The ball essentially pops off the ends of these extended fingers. This linear, forward driving motion is the final guarantee that no rotational force, or as little as humanly possible, is applied to the ball. To appreciate the sheer delicacy of this moment, you only need to look at the immense care knuckleballers take with their primary point of contact, their fingernails. R.A. Dickey was famous for his meticulous fingernail maintenance. He needed them to be filed perfectly, kept at a precise length, and strong enough to withstand the immense pressure of being driven into the ball seams over 100 times a game. Why? Because the hard, smooth surface of the fingernail provides a lower friction release point than the soft, fleshy pad of the fingertip. When the ball is pushed off the nails, it is less likely to grab or catch on the skin, which could impart a tiny, accidental spin. The image of a pitcher filing his nails in the dugout isn't a sign of vanity. It's the equivalent of a surgeon sterilizing their instruments. It's a mission-critical part of ensuring a clean, spin-free release. This all serves to debunk the persistent myth of the easy motion. Because the pitch is slow and lacks that violent, explosive finish, many people assume it's a lazy or low-effort delivery that any aging player could adopt. The truth is that the motion is biomechanically bizarre and incredibly difficult to repeat consistently. The human body wants to complete the kinetic chain. Resisting that natural urge pitch after pitch requires a unique kind of strength, not explosive power, but the strength of rigidity and restraint. Furthermore, the penalty for failure is absolute. If a fastball pitcher's release is slightly off, they might miss their spot by a few inches. If a knuckleball pitcher's wrist breaks by even a single degree, the spell is broken. The most unpredictable pitch in baseball instantly becomes the most predictable and hittable. A flat, 70 miles per hour batting practice fastball right down the middle of the plate. Herein lies the paradox. The softest, most delicate pitch in the game requires the most rigid discipline and the most absolute consistency at the moment it is set free. And perhaps no one in the modern era embodied the paradox of soft touch and rigid discipline better than the late, great Tim Wakefield. For nearly 2 decades, his signature pitch wasn't just a knuckleball. It was an event. It was appointment television. It had a name that perfectly captured its essence, the butterfly, and watching it float to the plate was to watch a master artist at work, painting on a canvas of air with a palette of pure chaos. If you want to understand the soul of the knuckleball, you have to understand the career of Tim Wakefield. His story itself is a testament to the knuckleball's power as a career-altering force. Wakefield wasn't some hotshot pitching prospect who developed a trick pitch. He was a struggling minor league first baseman in the Pittsburgh Pirates organization. He had some power, but he wasn't hitting enough to project as a major leaguer. His career was, for all intents and purposes, stalling out, but in practice, he would often throw a knuckleball just for fun, a pitch his father had taught him. A coach saw the incredible, natural movement he got on the ball and made a suggestion that must have sounded insane at the time. Forget hitting and become a pitcher. This wasn't a gradual transition or the addition of a new pitch to an existing arsenal. It was a complete and total career reinvention, and all a bet on the strangest pitch in the sport. Within 2 years, he was in the major leagues, baffling hitters. What made Wakefield's knuckleball so iconic was its classicism. It was the archetype. He wasn't trying to overpower anyone. His pitch lived in that perfect 64 to 68 mile/hour sweet spot. It would come out of his hand and seem to rise on an invisible thermal updraft, arcing high before beginning its descent. And on that descent, the dance would begin. It would dip, dart, swerve, and shudder, all with a gentle, almost lazy grace. The nickname the butterfly was perfect. It was in the angry knuckleball that our Dickey would later popularize, which broke with a violent, sharp tremor. Wakefield's pitch fluttered. It was mesmerizing to watch, and for hitters, it was a waking nightmare. His mechanics were a study in simplicity and repetition. He used that classic defingered grip, digging the nails of his index and middle fingers into the wide horseshoe seam. His wind-up and delivery were smooth, economical, and devoid of any wasted motion. He would rock, lift his leg, and deliver the ball from a consistent 3/4 arm slot. Time and time again, this mechanical consistency was his foundation. By keeping every aspect of his body's motion as identical as possible from one pitch to the next, he minimized the variables he could control. This, in turn, allowed the variables he couldn't control, the whims of the air, the orientation of the seams, to completely take over and dictate the ball's flight, and crucially, his arm speed. When he threw his slow, 75 miles/hour fastball was virtually indistinguishable from his knuckleball delivery, which was the final layer of deception that kept hitters perpetually off balance. But to truly appreciate his legacy, you have to look beyond the physics and see the competitor. Look no further than Game 5 of the 2004 American League Championship Series. The Boston Red Sox were in the midst of their historic comeback against the New York Yankees, having just won a marathon extra inning game the night before to stave off elimination. Their bullpen was completely exhausted. Wakefield, who had been hit hard in his Game 1 start, was available for long relief. The game went into extra innings, and in the bottom of the 12th, in a hostile Yankee stadium with the season hanging by a thread, manager Terry Francona called his number. What followed was the stuff of legend. Wakefield took the mound and pitched 3 perfect, scoreless innings. He threw almost nothing but that 68 miles/hour butterfly. The Bronx Bombers, one of the most fearsome lineups ever assembled, were rendered utterly helpless. They swung through it, took it for called strikes, and made weak, bewildered contact. He was the calm in the center of the storm, a pitcher throwing a pitch with no velocity in a moment that demanded everything. The Red Sox would go on to win in the 14th inning, and that victory served as the bridge to the greatest comeback in baseball history. That performance cemented the knuckleball's place not as a sideshow act for eating up innings in May, but as a legitimate, championship-caliber weapon that could dominate the best hitters in the world when the stakes were at their absolute highest. This points to the deeper insight of Wakefield's career. Beyond the mystique of the pitch itself, the common narrative often paints knuckleballers as curiosities. Wakefield's legacy is one of profound durability and unwavering team-first value. The low-stress nature of the pitch on his arm allowed him to pitch effectively until he was 45 years old, compiling over 3,000 innings for the Red Sox. He was the ultimate safety net. He could start a game, pitch in long relief, get a key out in the 7th, or even close if the team was in a bind. He would willingly take the loss in a blowout game to save the arms of the other bullpen members for the next day. He was, for 17 seasons in Boston, a foundational, stabilizing force. The knuckleball didn't just define his unique style, it enabled a career of unprecedented longevity, versatility, and quiet leadership. He was the anchor in the storm, and his pitch was the storm itself. And if the pitcher's mound is the calm center of the storm, then the batter's box is pure, abject chaos. We've spent a lot of time analyzing the physics from the pitcher's perspective, but now we have to take that 60-foot, 6-inch walk to the other side. We have to step into the cleats of the hitter, stare out at that strange, floating apparition, and try to comprehend what is arguably the single most difficult task in all of professional sports. Trying to hit a knuckleball. To understand why it's so hard, you have to first understand that hitting a baseball is not a simple act of reaction. It's an act of prediction. A hitter's brain is a ridiculously powerful supercomputer. In the first fraction of a second after the ball leaves the pitcher's hand, that computer takes in a flood of initial data: the release point, the arm angle, the velocity, and most importantly, the spin of the seams. It then processes this data and runs a complex physics calculation to predict the exact three-dimensional point in space where the ball will be in about 400 milliseconds. The swing isn't launched at the ball, it's launched at that predicted future location. The knuckleball destroys this entire process. It is a pitch built on feeding the brain faulty data. The initial information it provides is a lie. The hitter sees a slow, 68 miles per hour pitch coming out of the hand with no spin. The brain's prediction model, based on a lifetime of experience, screams slow, straight, batting practice fastball. It calculates a trajectory and tells the muscles to prepare for a pitch arriving. Belt high on the inner half of the plate, the hitter begins to launch their swing at that predicted point. But then, as we know, in the last 15 feet of its flight long after the swing has been initiated, the ball is chaotic. Dance begins. It dives 6 inches and darts a foot outside. The pitch that arrives is not the pitch that the brain predicted. The supercomputer has crashed. The failure is even deeper at the neurological level, right down to how our eyes work. Your eyes don't track a moving object in a smooth, continuous film like a video camera. They make a series of incredibly rapid jumps called saccades, taking quick snapshots of the object's location. In between these snapshots, your brain fills in the blanks, creating the illusion of smooth motion. When tracking a spinning fastball or curveball, the brain can use the spin and the predictable trajectory to accurately guess where the ball will be at the next snapshot. But when tracking a knuckleball, the brain's guess is always wrong. The ball is never where it's supposed to be. The hitter is constantly trying to recalculate based on new, chaotic information. The result is a complete breakdown in visual tracking in a very real sense. The hitter is often swinging at a memory, the ghost of where the ball was on the previous snapshot, not where it actually is. This neurological assault is matched by an equally potent psychological one. Elite athletes are masters of pattern recognition and control. The knuckleball offers neither. There is no pattern. There is no control. This induces a feeling of profound helplessness that can be incredibly frustrating and mentally taxing. Then there's the humiliation factor. It's one thing for a powerful slugger to strike out on a blazing 98 miles per hour fastball. It's another thing entirely to flail wildly and miss a 68 miles per hour pitch by 2 feet, ending up corkscrewed into the ground. It looks foolish, and professional athletes hate looking foolish. This embarrassment can get into a hitter's head, causing them to press, to overswing, and to abandon any coherent approach. So what is the approach? How do hitters even try to solve this unsolvable problem? You'll see the main strategies, neither of which is particularly effective. The first is the power hitter's approach. Their natural instinct is to be patient, let the ball travel deep into the hitting zone, and then unleash their explosive power. But the knuckleball's slow speed is a form of temporal sabotage. It makes them feel like they have all the time in the world, which often causes them to start their powerful swing far too early, resulting in a weak rollover ground ball. Or they wait, and then the ball's late. Vicious break happens inside their swing, and they miss it completely. The second strategy is that of the contact hitter. This is generally the more successful approach, if you can call it that. They surrender any idea of driving the ball for power. They choke up on the bat, shorten their swing to its absolute minimum, and their only goal is to make contact, any kind of contact. They are just trying to poke the ball, to punch it, to get the barrel of the bat somewhere in the vicinity of the chaos and hope that it hits something. It is a strategy of pure survival. As former slugger Paul Konerko once said, the only advice that works is, when you see it, hit it. You can't wait. You have to be aggressive and hope you hit it. It's an admission of defeat, a surrender to pure chance. You'll sometimes hear a frustrated fan or analyst propose a seemingly logical, if radical, solution: just stand there and let it hit you. Take one for the team. This reveals a fundamental misunderstanding of the hitter's plight. Firstly, a 70 miles per hour pitch, even a knuckleball, still hurts. But more importantly, it's psychologically and neurologically impossible. A hitter's entire being, every fiber of their muscles and every synaptic firing in their brain, has been trained for over 2 decades to do one thing: see ball, hit ball, to consciously override that lifetime of ingrained instinct and not swing at a pitch that, for the first 40 feet, looked like the most perfect meatball they'll ever see. Would require an almost superhuman level of mental discipline, and even if they could manage it, the pitch is so erratic it might just move out of the way, dancing back over the plate for a strike. There is no right way to hit a knuckleball. There is only the attempt, the swing, and the hope that, for one fleeting moment, the chaotic universe of the pitch aligns with the simple plane of the bat. But if the hitter's task is a desperate act of hope, the job of the person squatting directly behind them is an exercise in pure, unadulterated punishment. We now turn our attention to the unsung, often battered, and perpetually bruised hero of the knuckleball saga, the catcher. To put it plainly, their job is, in many ways, even harder than the hitters. It is a 60-foot, 6-inch journey into agony, and it requires a unique combination of bravery, skill, and a complete surrender to the absurd. Let's consider the fundamental differences in their tasks. The hitter, for all their struggles, has the advantage of weaponry. They are wielding a 33-inch long to 0.5-inch diameter wooden barrel. Their goal is simply to make contact somewhere on this relatively large surface area. The catcher, on the other hand, is trying to secure that same chaotic 5-ounce projectile cleanly in the small pocket of a leather glove. The margin for error is not just smaller, it's microscopic. A hitter can be a few inches off and still foul a pitch off. If a catcher is a few inches off, the ball is ricocheting off their shoulder and rolling to the backstop, while the go-ahead run scampers to third base. Furthermore, the catcher's job isn't just to stop the ball. They are also responsible for framing and receiving the pitch in a way that makes it look like a strike to the umpire. How on earth do you frame a pitch that you have no idea is coming? A catcher will set up their glove in the middle of the plate, expecting the 68 miles per hour floater. But the pitch that arrives is a 68 miles per hour dart that dives into the dirt a foot and a half to the left. The very concept of framing becomes a joke. The goal shifts from artistry to pure survival. This grim reality is reflected in the specialized tools of the trade. Catchers tasked with handling a knuckleballer often abandon their sleek, modern catcher's mitts in favor of much larger, almost comical-looking gloves. Tim Wakefield's personal catcher, Doug Mirabelli, famously used what was essentially a first baseman's mitt, and other knuckleball catchers have used softball mitts or specially designed models nicknamed the claw. These weren't designed for a crisp, satisfying pop in the pocket. They were designed for absorption. The goal was less to catch the ball in the traditional sense and more to trap it, to smother it, to do anything possible to keep it from getting past. The value of a catcher who could even marginally succeed at this task was immense. The Boston Red Sox were so dependent on Doug Mirabelli to handle Wakefield that they famously traded for him in the middle of a game in 2006, flying him on a private jet and giving him a police escort to the ballpark just in time for him to suit up and catch that night's start. But if you want the cold, hard data to prove the impossibility of the task, you only need to look at one statistic: the pass ball. A pass ball is a pitch that the catcher fails to control. With ordinary effort, allowing a runner to advance, it is an error charged directly to the catcher. The record books for this particular stat are not just peppered with the names of knuckleball catchers. They are completely dominated by them. The all-time records for pass balls in a single season, in a single game, and even in a single inning all belong to the poor souls who had to squat behind the likes of Hoyt Wilhelm, Phil Niekro, and Charlie Huff. Bob Booker, who famously had the pleasure of catching for Niekro, perfected the gallows humor required for the job. His advice for catching the knuckleball: wait till it stops rolling, then go to the backstop and pick it up. It's not an indictment of their skill. It's a testament to the pitch's chaos. These were often elite defensive catchers who were made to look like amateurs. On days their knuckleballer took the mound, the 1987 Toronto Blue Jays had the knuckleballers on their staff, and their primary catcher, Buck Martinez, set a franchise record for pass balls that will likely never be broken. This reveals a deeper insight into the craft. Catching a knuckleball isn't about having quicker hands. It requires a complete and total philosophical rewiring of the art of catching. A conventional catcher is taught to be strong and firm with their hands, to stick the pitch where it crosses the plate. A knuckleball catcher must learn to be the opposite. They have to be soft, receptive, and reactive. They have to abandon the idea of perfect presentation and adopt the body as a backstop mentality. Their number one priority on every single pitch is simply to keep the ball in front of them. By any means necessary, They expect to miss it with their glove. The entire technique becomes about anticipating the miss and using their chest protector, their shin guards, and their mask as a last line of defense. It's an unglamorous, often painful, and sprawling style of catching. It is a shared burden between pitcher and catcher, an unspoken agreement that chaos is coming. The pitcher trusts that the catcher will sacrifice his body to stop the pitch, and the catcher trusts that the pitcher, well, the catcher just hopes the pitcher gets it somewhere in his general vicinity. It is the ultimate battery relationship, forged in the fires of shared unpredictability. But there's a third party in this chaotic triangle, an impartial observer who stands just inches from the action, tasked with the Sisyphean chore of imposing order on this unpredictability. We're talking, of course, about the home plate umpire. And while they don't have to swing a bat at the knuckleball or try to stop it with a glove, their job to legislate the strike zone might be the most thankless and mentally exhausting of all. They are asked to apply the rigid, geometric rules of baseball to a pitch that behaves as if it's from another dimension. To understand the umpire's ordeal, you have to appreciate the fundamental nature of the strike zone. According to the rulebook, the strike zone is a two-dimensional plane, a vertical rectangle that sits directly over home plate. With its boundaries defined by the batter's stance, the rule is, in theory, simple. Did any part of the baseball pass through any part of that rectangle? For 99% of pitches, this is a manageable, if difficult, question to answer. A fastball, a slider, a curveball, they all travel on relatively smooth, predictable arcs. An umpire is trained to pick up the ball out of the pitcher's hand, track its trajectory, and make an accurate judgment of where its path will intersect that two-dimensional plane. The knuckleball makes a mockery of this process. Its flight path is not a smooth, predictable arc. It's a jagged, erratic scribble. This creates a nightmare for the umpire. A pitch can spend the first 50 feet of its journey looking like it will be a foot outside, causing the batter to relax and the umpire's brain to categorize it as a ball. Then, in the last 10 feet, it can take a sudden, violent swerve and clip the back corner of the plate. Conversely, a pitch can look like a perfect, down-the-middle strike for its entire flight, only to take a precipitous dive just inches before it crosses the front plane of the plate, ending up in the dirt. The core of the problem is that the umpire must judge the ball's location at the precise, infinitesimal moment it cuts through the plane of the plate. With a knuckleball, the ball as positioned a foot in front of the plate can be radically different from its position a foot behind the plate. The umpire is forced to make a high-speed judgment on an object whose defining characteristic is that its location at any given moment is a surprise. This visual chaos is compounded by the human elements of umpiring. An umpire is trained to get into a low, stable, athletic set position, keeping their head as still as possible to create a consistent vantage point. But the knuckleball-esque wild dance can instinctively cause an umpire-esque head and eyes to flinch and move, throwing off their entire system of perception. Furthermore, umpires rely heavily on the catcher's glove as a crucial reference point. A good catcher receiving a fastball on the back of the plate reinforces the umpire's call. But as we just discussed, the knuckleball catcher is a study in desperation. Their glove is rarely a stable target. It's a moving, lunging, sprawling last line of defense. The catcher's chaotic movements effectively unframe every pitch, stripping the umpire of their most reliable landmark and making even a perfect strike look like a wild miss. Let's put you in the umpire's mask for a classic pitch sequence. The first pitch is a knuckleball that starts a foot outside to a right-handed hitter. The batter sees it and immediately gives up on it. Your brain, as the umpire, is already logging it as ball, but in the final few feet, the pitch breaks hard and catches the very edge of the outside corner. The catcher, who was set up inside, makes a desperate, lunging stab across his body to snag it. You have to make the call. Did it clip the black? You trust your eyes. You ring him up. Strike 3. The batter is livid, slamming his bat. From his perspective, the pitch was never close. The manager is storming out of the dugout. You are left to defend a call based on a last-second geometric miracle. On the very next pitch to the next batter, the knuckleball starts right down the pipe. It looks like the easiest strike call you'll make all day, but this one dives. It dives so sharply that it bounces in the dirt before it even reaches the catcher's glove. The batter swings over the top of it. Now you have a different kind of chaos to legislate. Was it a swinging strike? Did the catcher catch it cleanly on the short hop for the out? Did it take the bat for a foul tip? It's a confusing mess of flying dirt, a bouncing ball, and sprawling bodies, and you have to make the definitive ruling. This leads to a common complaint you'll hear from hitters and fans, that umpires give knuckleball pitchers an overly generous, wide strike zone. While there may be some truth to this perception, the deeper insight is that it might not be conscious generosity so much as a subconscious survival mechanism. Faced with a pitch that is so fundamentally difficult to track, an umpire's brain might naturally widen its definition of a strike, giving the benefit of the doubt to any pitch that is reasonably close. They know the impossible task the catcher is facing, and that can't help but influence their judgment. In the end, the knuckleball strike zone is often less a reflection of the rulebook and more a testament to the umpire's sheer ability to make a reasonable inference. In the face of visual anarchy, it presents the ultimate challenge to the coming era of automated strike zones. Can a camera and a computer accurately legislate a pitch that seems to actively defy the laws of predictable physics? And if Tim Wakefield's classic slow-moving butterfly represented one end of the knuckleball spectrum, the gentle, mesmerizing artistic side, then the other end of that spectrum was personified by a former journeyman pitcher who reinvented not just his own career, but the very perception of the pitch itself. He took the knuckleball and imbued it with a power pitcher's mentality, right in a faster, more violent, and more aggressive version of it, all the way to a Cy Young Award. We're talking about our A. Dickey and his signature creation, the angry knuckleball. For decades, the knuckleball was typecast. It was a slow pitch, a soft pitch, a finesse pitch. Wakefield was the master of this archetype. His ball lived in the mid-60s, fluttering and dancing with a high arc. Dickey shattered that mold. His knuckleball was routinely clocked between 75 and 80 miles per hour, and he could even touch 82 or 83 when he needed to. In the world of the knuckleball, that 10 to 15 miles per hour difference is a Grand Canyon-sized chasm. The movement it produced was entirely different. Where Wakefield's pitch fluttered, Dickey's trembled. Where Wakefield's pitch danced, Dickey's darted. It was a pitch with a much later, sharper, and more vicious break. It didn't float like a butterfly. It behaved like an agitated hornet, buzzing in on a hitter before taking a sudden jag turn. The angry moniker, which Dickey himself embraced, was a perfect description. It wasn't a pitch of gentle deception, it was a pitch of outright aggression. So how did he achieve this unprecedented velocity while still killing the spin? The answer lies in his unique background and his ferocious mechanics. Unlike Wakefield, who was a failed position player, R.A., Dickey was a former first-round draft pick, a conventional power pitching prospect for the Texas Rangers. His career was famously sidetracked when a team doctor discovered he was born without an ulnar collateral ligament UCL in his right elbow, the very ligament that is famously replaced in Tommy John surgery. Despite being able to pitch, the diagnosis scared teams, and he spent the next decade as a fringe, up and down major leaguer. It was only in his early 30s, as a last resort, that he fully committed to the knuckleball, but he brought his power pitcher's body and mindset. With him, his delivery was far more violent than Wakefield's smooth, economical motion. He drove hard with his legs and rotated with his torso, using the full force of his athletic frame, and his grip and release were, for lack of a better word, ferocious. He dug his fingernails into the seams with such force that he had to develop a grueling conditioning regimen for his fingertips just to prevent them from breaking down. His release wasn't just a gentle push, it was a powerful shove, an explosion of force directed straight through the baseball. He lived on that precarious aerodynamic razor's edge, throwing the ball as hard as he possibly could without pushing it out of the critical chaotic regime. The ultimate proof of concept for this radical new approach came in his historic 2012 season with the New York Mets. The statistics he put up were simply staggering. He won 20 games for a mediocre team, posted a sparkling .73 ERA, and led the entire National League with 230 strikeouts. That strikeout number is the most telling detail. Historically, knuckleballers are soft contact specialists. They survive by inducing weak ground balls and lazy pop-ups. They are not strikeout artists. Dickey's ability to miss bats at such an elite rate proved that his hard knuckleball wasn't just a curiosity, it was a legitimate, top-of-the-rotation, swing and miss weapon. For a stretch in June of that season, he was perhaps the most dominant pitcher on the planet, throwing back-to-back one-hit shutouts. It was a run of utter mastery that defied everything the league thought it knew about his chosen craft. At the end of the season, he was awarded the Cy Young Award, becoming the first knuckleball pitcher in history to receive the honor. Now, after hearing that, you might logically conclude that Dickey's harder, better, faster, Stronger versions simply made the old model obsolete. Why would anyone ever throw a 68 miles per hour knuckleball again? But the deeper insight lies in the trade-off. Dickey's method was a high-wire act with an incredibly thin margin for error. By throwing the pitch at such a high velocity, he was constantly flirting with the edge of disaster. If his release point was off by even a fraction, if his wrist broke by a single degree, he would impart a slight spin onto the ball. A spinning 80 miles per hour pitch with no real break is one of the most hittable pitches in baseball. His highs, as evidenced by his Cy Young season, were stratospheric, but his bad days could be equally spectacular in their failure. He gave up a lot of home runs when the pitch was flat. Dickey's success didn't invalidate the Wakefield model. It simply expanded our understanding of what the knuckleball could be. It proved the pitch wasn't a monolith, but a spectrum. His approach was a perfect, unique marriage of his personal history, a power pitcher-esque body, and aggressive mentality. With the bizarre physics of a spin-free baseball, he didn't just adopt the knuckleball as a last resort. He adapted it to his own specific athletic gifts, creating a ferocious hybrid that the sport had never seen before and may never see again. But whether you're throwing Tim Wakefield's 68 mile per hour butterfly or RA, Dickey's 80 mile per hour Hornet, the physical mechanics, the aerodynamics, and the years of practice are only half the battle. To truly succeed with this pitch, to build a long, endurable career on a foundation of chaos, a pitcher must master something far more elusive than a spin-free release. They must master the mental game. They have to be willing to stare into the void of unpredictability, pitch after pitch, inning after inning, and not just accept it, but fully and truly embrace it. To understand the knuckleballer's unique psychological profile, you first have to understand the mind of a conventional pitcher. Every other pitcher in baseball is, in the best possible sense of the term, a control freak. Their entire existence is a quest for precision and command. They spend thousands of hours learning to hit a target the size of a dinner plate from 60 feet away. Their success and their value are measured by their ability to execute a plan, to command the baseball, to impose their will upon it. When they miss their spot, they get angry. When they hit it, they feel a sense of mastery. The knuckleballer must perform a complete and total rejection of this mindset. It is the core requirement of the job. Their goal is not to command the ball, but to unleash it. They must learn to separate the process from the outcome. Their entire focus is on controlling the things they can: the grip, the arm slot, the stiff wrist, the push release. But the moment the ball leaves their fingertips, they must surrender all ownership of the outcome. They have to accept that they have just launched a chaotic system whose final destination is fundamentally unknowable, even to them. It's the difference between being a sniper and a falconer. The sniper controls every conceivable variable: windage, elevation, breathing to ensure the bullet hits a precise, predetermined point. The falconer trains the bird, nourishes it, and then releases it, trusting in its nature to hunt, but never knowing the exact path it will take through the sky. So how does an elite athlete, a person whose career is defined by results, cope with this fundamental lack of control over the results? They have to develop an almost Zen-like discipline. They cannot allow themselves to get too elated by a swinging strikeout, nor too dejected by a walk on a pitch that breaks a foot and a half outside. They have to understand on a deep and intuitive level that a certain amount of bad chaos, the pass balls, the wild pitches, the walks, is the non-negotiable price of admission for good chaos. The foolish swings, the weak contact, the confused hitters. It is a package deal. To get emotional about the outcome of any single pitch is a recipe for disaster, because that emotion can seep into the mechanics and disrupt the one thing they can control: the perfect, spin-free release. Their definition of success has to change. For a fastball pitcher, success is a dot in the catcher's glove. For a knuckleballer, success is a feeling in their fingertips. It's a perfect release. And where the ball goes after that is in the hands of the gods of aerodynamics. Imagine the sheer mental fortitude this requires during the inevitable bad outing. The knuckleballer takes the mound, and from the first pitch, it's clear it's not their day. The air is thin, or their release is just a fraction off. The pitch isn't dancing, it's floating. The first batter hits a line drive home run. The next batter walks on for pitches that weren't even close. A runner gets on, and the next pitch sails to the backstop. An inning can snowball into a catastrophe in the blink of an eye. A conventional pitcher in this situation might try to bear down, to reach back for more, to throw harder, or be finer with their location. A knuckleballer cannot do this. Trying to aim the knuckleball, to guide it, to take a little off or add a little to it, will only make it worse by introducing spin. Their only option in the face of total failure is to take a deep breath, quiet their mind, and execute their next pitch with the exact same mechanics and the exact same trust in the process. Even when all the recent evidence suggests the process is failing them, the ability to do that, to come back 5 days after a disastrous start and throw that first knuckleball of the next game with the same unwavering belief, is the truest mark of their mental strength. This is why it is a mistake to view this surrender of control as a passive or lazy mindset. It is not a shrug of the shoulders and let us just chuck it up there and see what happens. It is an active, courageous, and deeply held faith. It's a faith in the physics that they have studied. It's a faith in the thousands of hours they have spent in lonely bullpen sessions, honing that unnatural, rigid release. A knuckleballer makes an active choice on every single pitch to believe that over the long run, the laws of chaos will bend in their favor more often than they bend against them. It is a calculated gamble on the nature of reality itself. This is why you see such interesting, adventurous personalities among knuckleballers. It is a mindset that attracts those who are comfortable with, and perhaps even drawn to, the great unknown. And it turns out that this profound, almost philosophical unpredictability isn't just a challenge for the human mind of the hitter, the catcher, and the umpire in our modern, data-driven era of baseball, where every single pitch is tracked, measured, and cataloged with astonishing precision. The knuckleball presents an equally profound challenge to our most advanced technology. The ghost in the machine, it seems, is also a ghost of the machine. Over the last 2 decades, baseball has undergone a data revolution. Every major league ballpark is now equipped with sophisticated tracking systems, whether it's the Doppler radar-based TrackMan or the high-speed camera-based Hawkeye system. These technologies are the engines of modern baseball analytics. They measure dozens of variables for every pitch, its exact velocity out of the hand, and over the plate, its precise release point, its spin rate in revolutions per minute, the axis on which it spins, and the horizontal and vertical break it exhibits. This is the data that generates the on-screen graphics you see during a broadcast, and the mountains of spreadsheets that front offices use to evaluate players and build game plans. At their core, all of these systems function on a principle of predictive modeling. They capture the initial dozen or so feet of the ball's flight, and then, based on those initial conditions, primarily velocity and spin, they use a sophisticated physics model to project the remainder of its trajectory. This model is built around the 3 dominant forces that act on a conventional pitch: gravity, drag, and the spin-induced Magnus effect. For 99.9% of pitches, this model works beautifully, but the knuckleball breaks the model in every conceivable way. The first and most obvious problem is the spin input. These complex algorithms are fundamentally built on the assumption that spin is the primary driver of movement. When a knuckleball is thrown, the system measures a spin rate that is functionally 0, maybe 50 or 80 RPM. The predictive model sees this number, finds no significant Magnus force to account for, and essentially short circuits. It predicts a simple, gravity and drag influence arc, a slow, lifeless pitch with no break. It is predicting a reality that will not occur. The result is that the data these systems produce for a knuckleball is notoriously messy and unreliable. The system tracks the ball's actual, erratic path and then tries to retroactively fit that chaos into its neat and tidy boxes of horizontal break and vertical break. It can't. It's trying to describe a frantic scribble using only straight lines. You'll often see the on-screen graphics for a knuckleball look completely bizarre, while a Clayton Kershaw curveball will be mapped with a perfect, smooth arc. The graphic for a knuckleball might be a series of jagged, disconnected lines. Sometimes the system gives up entirely, showing a simple straight line with a data unavailable message. It's the technology throwing its digital hands up in surrender. This visual discrepancy is a real-time demonstration of the technological problem. The system is trying to describe a butterfly's flight using the language of cannonballs. The core assumption of the technology is that a pitch is a ballistic object whose path is predetermined at the moment of release. The knuckleball violates this assumption. It is not a ballistic object in the same sense. It is an object whose trajectory is being actively and randomly altered throughout its flight by a series of tiny, unpredictable aerodynamic events. The physics model that works for the entire rest of the sport simply does not apply here. Given all this, you might assume that modern technology is the enemy of the knuckleball, that it's a tool that has no use for this archaic art form. But here lies a fascinating paradox. While the tracking technology that measures the result of the pitch struggles, other modern tools Specifically, high-speed cameras like the Aerodynamics might actually be the key to making it easier to learn the pitch. Think about it. For generations, learning to throw a knuckleball was a mystical process based on feel. A pitcher would throw, and the only feedback they would get was from the catcher saying, "That one danced," or "That one spun a little." It was a slow, frustrating process of trial and error. Today, a pitcher can go into a training facility, throw a knuckleball, and instantly see a super slow motion replay of their release, captured at thousands of frames per second. They can see, with microscopic precision, exactly how the ball left their fingertips. Did the wrist break even a little? Did the index finger drag across the seam, imparting a slight rotation? Did the ball push cleanly off the fingernails? This technology provides immediate, objective, visual feedback, dramatically shortening the learning curve. So in a strange twist of fate, the same technological revolution that fails to quantify the knuckleball as chaotic flight might be the very thing that makes it easier for a new generation of pitchers to master the art of summoning it in the first place. But even if modern technology does make the knuckleball easier to learn, a young pitcher who chooses to walk this path still has to overcome the single biggest hurdle of all: the deep-seated institutional skepticism that has followed this pitch for over a century. This brings us to the central debate about the knuckleball's very identity, a question that has been argued in dugouts, front offices, and barrooms for generations. Is it a legitimate, top-tier weapon in a pitcher's arsenal, or is it just a gimmick? Is it a high art, or is it a circus trick reserved for those who can't make it as real pitchers? To be fair, you can understand where the skeptics are coming from. Their argument usually rests on three main pillars. The first, and most powerful in the modern game, is the velocity argument. Baseball, now more than ever, worships at the altar of the radar gun. Pitchers are assets, and their value is often directly correlated with their ability to throw a baseball at speeds approaching 100 miles per hour. In this cultural context, a pitch that deliberately tops out at 70 miles per hour seems archaic, non-competitive, and fundamentally soft. Is often perceived as a sign of weakness, a last resort for an arm that can no longer handle the rigors of power pitching. The second pillar of the gimmick argument is its perceived lack of seriousness. The very nature of the knuckleball, the comical flailing of the hitters, the sprawling agony of the catchers, the oversized mitts, the sheer absurdity of its drunken flight path contributes to a circus-like atmosphere. For some of baseball's purists, this feels like a departure from the noble, athletic confrontation of a power pitcher versus a power hitter. It's a novelty act, an entertaining diversion, but not the real game. And finally, for the analytically minded managers and front office executives, the pitcher's own admitted lack of control is a fatal flaw. Baseball is a game of percentages, of putting players in a position to execute a predictable outcome. A manager wants to know that with the game on the line, their pitcher can hit the outside corner with a slider on a 0 to count. A knuckleballer can offer no such guarantee. They can only promise to unleash chaos for a risk-averse organization. Investing millions of dollars in a pitcher who cannot promise precision feels like an unacceptable gamble. These are the arguments against it, but the case for the knuckleball as a legitimate, game-altering weapon is, I believe, far more powerful. First and foremost, the results speak for themselves. True gimmicks in sports have a very short shelf life. They work for a while, and then the league adjusts, the novelty wears off, and they disappear. The knuckleball has been getting elite professional hitters out for more than 100 years. It has produced multiple Hall of Famers like Hoyt Wilhelm and Phil Niekro, pitchers who won over 300 games with it. It has produced a Cy Young winner in R.A. Dickey. It has been a central weapon on multiple World Series championship teams, from Wilhelm's Giants and Orioles to Tim Wakefield's Red Sox. These are not the resumes of sideshow acts. Gimmicks do not win world championships. Second, throwing a knuckleball is not a sign of a lack of skill. It's the mastery of a different, and in many ways, more arduous discipline. As we've spent the better part of this analysis detailing the unnatural mechanics, the iron-willed mental fortitude, the years of lonely, frustrating practice required to perfect the spin-free release. This is a journey of immense difficulty. It's not a shortcut for those who can't pitch. It's a different and more treacherous mountain to climb. And third, in our current era of hyper-specialization, the knuckleball is the ultimate strategic mismatch. Hitters today spend their entire careers training against two things: high velocity and high spin. They take thousands of swings in high-tech batting cages that can simulate a 100 mph fastball or a 3000 RPM slider. What they cannot train for, what no machine can yet replicate, is the chaotic, spin-free flight of a knuckleball. A hitter in today's game might face a knuckleballer once or twice a season. If they're lucky, they are given absolutely no time to adapt. The pitch's greatest strategic strength in the modern game is its profound rarity. It doesn't just present a different look, it forces the opponent to play an entirely different sport, a sport for which they are completely and utterly unprepared. You can even see this principle at play when a position player is brought into pitch in a blowout. They will often lob 60 miles per hour knuckleballs to get through the inning. This is often cited as proof that it's a joke pitch, but what it really proves is that even a poorly thrown amateur or knuckleball is a better strategic option for getting outs with low velocity than a straight, slow fastball. Its fundamental principle, the absence of predictable spin, is a more effective weapon than velocity. When velocity is not an option, so is it a gimmick. Perhaps the knuckleball's greatest trick, its most effective deception, is its own reputation. The pitch wants you to think it's a gimmick. It wants the hitter to step into the box with a smirk, thinking, oh, this soft-tossing clown? I'm going to launch this into the upper deck. It is precisely that arrogance, that lack of respect for the sheer physics of the pitch, that leads to the frustration and failure. The best weapon is always the one your enemy underestimates. And for over a century, the baseball world has continued to underestimate the chaotic, the beautiful, and the devastatingly legitimate weapon that is the knuckleball. And the legitimacy of that weapon isn't just measured in strikeouts or error. It is measured by the powerful ripple effect of chaos it sends through every single strategic decision a manager has to make for all 9 innings. When a knuckleballer takes the mound, the standard, dog-eared playbook of baseball strategy gets thrown out the window. Their presence on the roster creates a domino effect that fundamentally alters the tactical landscape of the game, impacting everything from defensive alignments and base-running aggression to the delicate art of bullpen management. Let's start with the most immediate and obvious strategic shift, the defense. The first decision a manager makes on a knuckleball day is who is going to be catching. As we've discussed, this is a non-negotiable. You cannot send your all-star, power-hitting catcher out there if he can't handle the knuckleball. You are forced to play the specialist, the catcher who is most proficient at blocking and smothering the chaos, even if that player is a point-to-oh hitter who represents a black hole in the lineup. This is often a significant offensive downgrade, a sacrifice a manager makes before the first pitch is even thrown. Beyond the catcher, the entire defensive alignment has to be on high alert. Knuckleballers tend to induce a high number of fly balls, but they are not the majestic, towering fly balls hit off a fastball. They are often weakly hit, looping flares that die in the outfield grass, or swirling pop-ups that get caught in the wind. Outfielders have to play a shallower, more reactive style, knowing that judging the trajectory of these oddly hit balls is a nightmare. In the infield, players have to be prepared for an endless series of slow rollers, bizarre choppers off the plate, and swinging bunts. The predictable geometry of a hard-hit ground ball is replaced by the erratic bounces of a mished sphere. Standard defensive shifts based on a hitter's pull tendencies against hard stuff become less reliable. The entire defense must shift from a predictive mindset to a purely reactive one. For the opposing manager, the knuckleballer presents a unique set of offensive opportunities and dilemmas. The most obvious is on the base paths. A knuckleball is slow to the plate, giving runners a great jump, and the catcher, so singularly focused on the monumental task of just securing the pitch, is often a split second slower with their exchange and throw to second base. This is a green light. Opposing managers will almost always become hyper-aggressive, attempting to steal bases at a much higher rate than they normally would. The game can quickly turn into a track meet, with the knuckleballer's team essentially conceding stolen bases in the hope that the pitch will induce a rally-killing double play or a strikeout. Similarly, the bunt becomes a much more potent weapon. A slower pitch is easier to lay down, and the ever-present threat of a pass ball on a third strike makes even a strikeout a potential adventure. But the real chess match happens with the opposing manager's lineup and pinch-hitting decisions. Who do you want at the plate in a high-leverage situation in the 8th inning? Do you send up your best slugger, your 40 home run guy, knowing that his long, powerful swing is ill-suited to the knuckleballer's deceptive timing, and that he is likely to strike out looking foolish? Or do you opt for your pesky, light-hitting utility infielder, a player with a short, compact swing whose only goal is to make contact? Many experienced managers will choose the latter, completely upending their typical late-game substitution patterns. in favor of a contact over power approach. Perhaps the most complex strategic ripple effect is felt by the knuckleballer's own manager, specifically in how they manage their bullpen. A knuckleballer on a good day is a manager's dream. Their arm is so resilient and their motion so low stress that they can routinely throw 110, 120, even 130 pitches. A good knuckleball start can save an entire bullpen, giving all the key high-leverage relievers a full day of rest, which pays dividends for the rest of the series. But a bad knuckleball start is a manager's worst nightmare. If the pitch is flat and the knuckleballer gets knocked out in the second inning, the manager has to ask their hard-throwing relievers to cover 7 or 8 innings. This creates the knuckleball hangover effect. Hitters who have just seen 3 rounds of 70 miles per hour, floaters can be completely overwhelmed by the first 95 miles per hour fastball they see from a reliever. But just as often, after 1 or 2 pitches to adjust their timing, they are suddenly locked in, and that 95 miles per hour fastball look like a beach ball. It makes every pitching change a high-stakes gamble. All of this points to a fascinating truth about the knuckleball's place in the modern game. In an era dominated by analytics, where every decision is increasingly informed by massive data sets, the knuckleball is a ghost in the spreadsheet. You can't build a reliable statistical model when the sample size is a handful of at-bats per year. The data is effectively meaningless. The presence of a knuckleballer on the mound rips the spreadsheet out of the manager's hands and forces them to manage by instinct, by feel, and by gut. In an age that often trends towards strategic homogeneity, the knuckleball is a powerful, welcome force for chaos, diversity, and the beautiful, unpredictable art of managing a baseball game. And this ability to be a reliable, durable, strategic asset over the course of a long and grueling season is directly tied to the single greatest advantage the knuckleball provides to the person throwing it, the gift of time. In a sport that violently grinds down the arms of its most talented pitchers, often cutting brilliant careers short, the knuckleball is the closest thing baseball has to a physiological fountain of youth. It is a pitch that doesn't just defy hitters, it seems to defy the aging process itself. To understand why, you first have to appreciate the sheer, brutal violence of throwing a conventional, maximum effort pitch. When a pitcher unleashes a 95 mile per hour fastball, the forces exerted on their arm are almost beyond comprehension. At the point of maximum external rotation, the shoulder is stretched to its absolute limit. Then, as the arm accelerates forward at a rate of over 7,000 degrees per second, the fastest recorded human motion in sports, the torque placed on the inside of the elbow is immense. The ulnar collateral ligament, or UCL, is strained to its breaking point with every single pitch. This is why the dreaded Tommy John surgery has become a near epidemic in the sport. Pitchers' arms, quite simply, are not designed by evolution to withstand these forces thousands of times a year. It is a fundamentally unnatural and self-destructive act. Now, contrast that with the knuckleball delivery. As we've detailed, the entire goal of the mechanic is to kill the final, most violent links in the kinetic chain. There is no explosive forearm pronation. There is no violent wrist snap. The whip is intentionally deadened. Biomechanical studies have confirmed what seems intuitively obvious. The amount of torque placed on the elbow and the level of strain on the shoulder S rotator cuff are drastically lower when throwing a knuckleball. The forces are much closer to those of a simple, long-toss throw than a max effort pitch. It is, from a joint health perspective, a profoundly gentle way to deliver a baseball. The result of this low-stress motion is written all over baseball as record books in the form of unprecedented longevity. The list of pitchers who have remained effective into their early and even mid-40s is a very short and exclusive club, but it is a club that is heavily populated by knuckleballers. It is not a coincidence. Hall of Famer Hoyt Wilhelm, one of the game's first true relief aces, pitched until he was 49 years old. Charlie Huff, another stalwart of the craft, pitched until he was 46. Our case study, Tim Wakefield, was still a key member of the Red Sox rotation at age 45. But the ultimate testament to the knuckleball SA's defined properties is the career of Phil Niekro, Knucksy, as he was known, pitched in the major leagues until he was 48 years old. That alone is remarkable, but the truly staggering fact is this: Phil Niekro won 121 games after he turned 40. To put that into perspective, that is a Hall of Fame caliber career in and of itself for many pitchers. The legendary Sandy Koufax, one of the most dominant pitchers ever, won 165 games in his entire career. Phil Niekro won 73% of his Sandy Koufax career after the age that most power pitchers are retired and doing broadcast work. And he wasn't just coasting, he was a workhorse. In an era when starting pitchers were expected to finish games, he routinely threw over 300 innings a season, a workload that is completely unthinkable for any pitcher in the modern game. In 1979, at the age of 40, he led the league with 21 wins, 23 complete games, and an almost unbelievable 340 innings pitched. An arm throwing fastballs and sliders would have turned to dust. Under that kind of strain, Niekro's arm was preserved by the gentle, repeatable motion of his signature pitch. Now, this doesn't mean the pitch is completely without physical consequence. The idea that it's a no-stress pitch is a slight oversimplification. It would be more accurate to say that it's a different stress pitch. While the knuckleball spares the fragile ligaments of the elbow and shoulder, it relocates that physical strain to other, smaller parts of the body to maintain that rigid, claw-like grip for 120 pitches. A knuckleballer has to have incredible and resilient strength in their forearms, hands, and fingers. They are far more susceptible to nagging injuries like tendinitis in the forearm or split fingernails issues that R.A. Dickey famously battled. And of course, the rest of the body, the back, the hips. The knee still has to endure the strain of a full, athletic pitching delivery. You still have to be a world-class athlete to take the mound every fifth day, but the trade-off is undeniable. The fountain of youth effect is real, but it's specific. It's a fountain for the parts of a pitcher's arm that are most vulnerable, the parts that have a finite and non-negotiable number of violent throws in them before they break down. By dedicating their careers to the knuckleball, pitchers like Niekro, Wakefield, and Wilhelm were making a conscious choice. They were accepting a different, more manageable set of physical challenges in exchange for a career that could last decades longer than their hard-throwing peers could ever dream of. So this all leads to a very logical and frankly, very troubling question. If the knuckleball is a legitimate, time-tested weapon, if it can baffle the best hitters in the world, if it can win championships, and if it provides a physiological fountain of youth that allows a pitcher to have a career that lasts into their mid-40s, where have all the knuckleballers gone? Why, in an era of unprecedented pitcher injuries and rampant Tommy John surgeries, is this uniquely arm-saving pitch a dying art? On the verge of total extinction from the professional ranks, the disappearance of the knuckleball isn't an accident, nor is it because the pitch has suddenly become ineffective. It is the slow, predictable result of deep systemic pressures and institutional biases that have taken hold at every single level of the sport, from the grassy fields of Little League to the polished boardrooms of Major League Baseball front offices. The problem begins at the grassroots level, in the very ecosystem where young players are developed. Youth baseball, especially the highly competitive and increasingly professionalized world of travel ball, is dominated by one single, tyrannical tool, the radar gun. A 14-year-old who can touch 85 miles per hour is immediately identified as a prospect. He is coveted. He is given the best coaching. He is put on a path. A 14-year-old with a dazzling 55-mile-per-hour knuckleball is, at best, an amusing oddity. At worst, he's a liability. Coaches, who are often volunteers or are primarily focused on winning the weekend's tournament, have neither the time nor the specialized knowledge to teach the knuckleball's bizarre mechanics. It's a long, uncertain, and frustrating process. It is far easier and more efficient to teach a kid a basic curveball or slider to get outs now. Young players who experiment with the pitch are often explicitly told by their coaches to stop throwing that junk and learn to pitch the right way. The system is designed to find and cultivate projectable velocity, and the knuckleball is, by its very nature, the antithesis of that goal. Even if a young pitcher manages to survive this initial filtering process and gets drafted, their journey through an organization's minor league system is fraught with peril. It's often referred to as development hell. The first and most significant hurdle is the catcher problem. Every single team a knuckleballer plays for, at every level from single A to triple A, needs to have a catcher on the roster who is capable of handling the pitch. This is a massive logistical and financial commitment for an organization. It means dedicating a roster spot not just to the knuckleball pitcher, but to his personal knuckleball catcher, disrupting the development path of their other catching prospects. Furthermore, how does an organization even evaluate a knuckleballer's progress? The modern scouting and player development apparatus is built on quantifiable metrics that simply don't apply. Scouts are trained to look for velocity, clean mechanics, and sharp, late-breaking secondary pitches. A knuckleballer has none of these. Their minor league stat line will almost always look strange. They'll have a high walk rate, they'll lead the league in wild pitches and pass balls, but they might also have a sub 3.0 era because they induce so much weak contact. It's a square peg in a round hole, and most organizations simply don't have the patience or the institutional knowledge to figure out what to do with them. The career of Charlie Hager, one of the few knuckleballers to pitch in the majors in the 2000s and 2010s, is a perfect illustration of this struggle. He was a talented pitcher who bounced between 5 different organizations, never quite finding a permanent home. He would have a string of successful outings, and a team would get excited. But then he'd have a few bad starts, the pass balls would pile up, and the organization would lose faith, sending him back to the minor leagues or releasing him. His story is the story of the modern knuckleballer, a constant, lonely battle not just against opposing hitters, but for a roster spot and for the belief of his own team. A skeptic might listen to all this and argue that the knuckleball is dying for a simpler reason. It is just not as effective against today's bigger, stronger, more analytically savvy hitters. But the deeper and more ironic truth is that the knuckleball's decline is a symptom of the league's all-consuming velocity arms race, an obsession that has had devastating consequences for pitcher health. The same system that weeds out the 14-year-old knuckleballer is the one that encourages a 16-year-old to throw as hard as he physically can, leading directly to the epidemic of youth arm injuries. In the cold calculus of modern front offices, the high probability of a power pitcher needing 1 or 2 Tommy John surgeries is seen as an acceptable cost of doing business because the potential reward of high strikeout ace is so great. They would rather gamble on a succession of powerful but fragile arms than make a long-term, lower upside in their view investment in the development of a durable knuckleballer. The final bitter irony is that the knuckleball's greatest asset in the modern game, its ability to preserve a pitcher's arm, is precisely what makes it an outcast in a system that has come to view those arms as powerful but ultimately disposable commodities. But is that the final, grim chapter in the story of the knuckleball? Is this beautiful, bizarre, and historic pitch destined to become a museum piece, a black and white relic we only see in grainy old highlight reels? Or, just maybe, could we be on the verge of a quiet knuckleball renaissance? Could the very forces that are seemingly killing the pitcher relentless focus on analytics and the constant search for a competitive edge be the same forces that ultimately bring it back from the brink of extinction? To make the case for a knuckleball comeback, you have to look at the pitch through the lens of modern baseball economics. The holy grail for every smart front office is the pursuit of market inefficiencies. It is the core principle of Moneyball. Find the skills and assets that are highly valuable for winning games, but are currently being undervalued or ignored by the rest of the league. In the early 2000s, that inefficiency was on base percentage. Today, every team understands the value of a walk. The new market inefficiencies are harder to find, lurking in the margins, and there is arguably no asset in baseball more systemically undervalued and misunderstood right now than the knuckleball. Think about it. We've just spent a significant amount of time detailing all the institutional biases that work against it. Youth coaches discourage it. Scouting models can't properly evaluate it. Organizations fear the developmental risks. This widespread aversion creates a massive potential opportunity. A smart, forward-thinking, and data-driven organization could exploit this league-wide bias. They could, in theory, acquire or develop a knuckleball pitcher for a tiny fraction of the cost of a hard-throwing prospect, who comes with a much higher price tag and a much greater risk of a career-altering injury. From a purely analytical standpoint, the knuckleball is the perfect antidote to the current style of baseball. Today's game is dominated by the 3 true outcomes: the home run, the strikeout, and the walk. Hitters are swinging from their heels, trying to generate maximum launch angle and exit velocity on every swing. The knuckleball attacks this philosophy at its core. It is incredibly difficult to hit a home run off a 70-mile-per-hour pitch that moves unpredictably. The hitter has to generate all the power themselves. It induces weak, missed contact, forcing the defense to be involved in subverting the all-or-nothing approach. In an era where everyone is zigging towards power, the knuckleball is the ultimate zag towards chaos. Furthermore, the single biggest expenditure for any baseball team, both in terms of salary and lost potential, is pitcher injuries. The velocity arms race has come at a staggering cost. An analytically minded front office could look at this and see another inefficiency. A pitcher who can stay healthy and reliably provide 180,000 to 100 durable innings every single year is an asset of almost incalculable value, even if their era is a bit higher than a flame-throwing ace. And as we've established, the knuckleball is the single most reliable path to that kind of career-long durability. A smart general manager might run the numbers and conclude that the financial and roster stability provided by one successful, cost-controlled knuckleballer far outweighs the risks and costs of their development. So what would a modern, analytically driven attempt to revive the knuckleball look like? Imagine a team known for its innovation, like the Tampa Bay Rays. They could decide to create a specialized knuckleball academy at one of their minor league facilities. They would use their scouting department to actively seek out players who fit the right profile. Former position players with great hands, pitchers coming off arm injuries who can no longer throw hard, or even college pitchers with a natural feel for the pitch. They would hire a dedicated, full-time knuckleball coach, perhaps one of the retired masters of the craft. They would assign a dedicated catcher to the project, and crucially, they would use high-speed camera technology to provide immediate, data-driven feedback on the spin rate of every pitch, dramatically accelerating the learning curve. The goal wouldn't be to build an entire pitching staff of knuckleballers, but to try and produce one homegrown, cost-controlled, and durable major league pitcher every 5 to 7 years. It would be a long-term investment in a sustainable competitive advantage that other teams, caught in the trap of chasing velocity, could not easily replicate. So why isn't this happening already? If the logic is so sound, where's the renaissance? The final, and perhaps largest, hurdle is not analytical, it is cultural. The entire ecosystem of baseball, from the old school scout to the Ivy League GM, is built on a century of conventional wisdom. Velocity is exciting. A sharp slider is impressive. The knuckleball is weird. Overcoming this deep-seated cultural bias, the fear of the unknown, requires a truly brave and iconoclastic leader. It requires a general manager and a manager who are willing to look foolish in the short term, who can endure the skepticism of their peers and the media, and who can stick with the project through the inevitable developmental struggles. The future of the knuckleball, therefore, may not depend on the physics or the data, both of which make a compelling case. It may just depend on whether there is anyone in a position of power brave enough to once again embrace the beautiful, maddening, and logical chaos of baseball's most unique pitch, and whether that brave leader ever emerges to champion a new generation of knuckleballers or not. The pitch's legacy is already secure because, as we've unraveled over the course of this deep dive, the knuckleball is so much more than just a strange or anomalous pitch. It is a grand synthesis of nearly every element of the sport. It is a convergence of complex physics, intense human psychology, and high-stakes strategy. It is the beautiful, chaotic heart of what makes this game so endlessly and wonderfully fascinating. Let's retrace our steps one last time and put all the pieces together. It all begins with the human element, with a pitcher making a conscious decision to reject power in favor of deception. It begins with an act of profound discipline, the unnatural claw-like grip, digging the fingernails into the seams. It continues with a paradoxical act of biomechanics, a full, athletic delivery that is intentionally deadened at its violent conclusion by a locked wrist and a forward push, and it is sustained by an almost zen-like mindset, a complete and total surrender of control, where the pitcher must find peace in the process and detach themselves from the chaotic outcome. They are not commanding the baseball. They are merely creating the perfect conditions for it to be set free the moment that ball leaves the fingertips. It is no longer a tool, but an independent actor in a complex aerodynamic play. Its first act is one of subtraction. By killing the spin, the pitcher has surgically removed the powerful, predictable Magnus effect from the equation, creating a power vacuum. Into this void rush a collection of much subtler, more delicate forces. The ball, now a rudderless ship, tumbles slowly through the air, its 108 raised stitches acting as tiny, unpredictable rudders. These seams strip the thin boundary layer of air clinging to the ball surface, forcing it to separate from the leather in a constantly shifting, asymmetrical pattern. This imbalance creates the invisible hands of pressure that shove the ball in sudden, random directions. At the same time, the air flowing past the ball peels off its back in a semi-rhythmic, alternating pattern of vortices, the Kármán vortex streak giving the pitch its signature side-to-side wobble. All of this is possible only because the pitch is thrown in that narrow, slow velocity sweet spot, giving these forces time to act, and it can all be enhanced or muted by the density of the air itself on any given day. This intricate physical dance then sends a massive shockwave of chaos through the human side of the game. It crashes the predictive supercomputer inside the hitter's brain, turning one of the world's most skilled athletes into a confused, flailing novice. It forces the catcher into a desperate, sprawling ballet of survival, a thankless job of blocking and smothering that inflates their pass ball stats and bruises their body. And it presents the umpire with an impossible task: to apply a rigid, two-dimensional rule to a three-dimensional object that refuses to travel in a straight line, making every call an exercise in high-speed guesswork. So let's watch one final pitch together, but this time, seeing it all at once. The pitcher pushes the ball perfectly from his fingertips, his expression calm. For the first 20 feet, it floats. The seams crystal clear, an object seemingly free from the influence of spin. Then, a horseshoe seam tumbles to the top, tripping the boundary layer and creating a high-pressure wake that gives the ball a sharp, downward shove. As it enters the hitting zone, a Kármán vortex streak begins to form, and the ball shimmies left, then right. But just before it reaches the plate, the ball's rotation presents another seam to the side, disrupting that rhythm and causing one final, violent dart inwards. The hitter, who started his swing time for a pitch down the middle, is now helpless, his bat slicing through empty air. The catcher, who anticipated the dive, smothers the ball in the dirt. The umpire rings the batter up. A simple strikeout in the scorebook, but in reality, the conclusion of an incredibly complex story told in less than a second. After all this analysis, the question remains, why do we love it? Why are we so captivated by this one strange pitch? I think it's because the knuckleball is the ultimate underdog story, not of a player, but of a set of physical forces. In a game of titans throwing thunderbolts, it is the butterfly that somehow conquers all. It reminds us that success in sports and in life is not always about being the strongest or the fastest. Sometimes, it's about being the most clever, the most resilient, and the most willing to embrace a path that nobody else dares to walk. In a world that is increasingly measured, quantified, and predicted, the knuckleball is a beautiful and necessary reminder that there is still room for magic, for mystery, and for a glorious, unquantifiable chaos that keeps us all watching. So, what have we learned today? We've unraveled the knuckleball from the inside out, seeing how a simple lack of spin forces a baseball to become a slave to the subtle, chaotic forces of aerodynamics. We've seen how the 108 seams act as rudders, how the boundary layer separates asymmetrically, and how vortex shedding gives the ball its signature dance. But more than just the physics, we've seen the human story. We've explored the incredible mental fortitude required of the pitcher, the neurological breakdown it causes in the hitter, and the strategic chaos it unleashes on the entire game. The knuckleball isn't just a pitch, it's a complete, self-contained ecosystem of unpredictability. My challenge to you is this: the next time you're lucky enough to see a knuckleball, whether it's in a classic replay of Tim Wakefield or R.A. Dickey, or from a new, brave pitcher carrying the torch, don't just watch the ball. Watch the whole story. Watch the catcher's desperate preparation, the hitter's frustrated timing, and the umpire's intense focus. See the invisible forces at play and appreciate the beautiful, complex physics unfolding in real time. Understanding the why behind the what is what makes being a fan so rewarding. That's the final whistle for this episode. Until next time, keep watching the game.